Welcome to Science for Sleep, a quiet space where curiosity can gently unfold and the universe feels a little more intimate. Here, science moves at a relaxed and comfortable pace. Our focus for tonight is a single star, one you may have noticed without ever knowing its name. It glows with a faint red hue in the shoulder of the Orion constellation, a steady and ancient light that can be seen even through the glow of our towns and cities. For millennia, anyone who looked up at that star had little reason to give it a second thought. It was a bright, familiar point in the sky, behaving just as a star should. Then, not long ago, something about it began to shift. The change wasn't sudden or dramatic. There was no brilliant flash or explosion to capture immediate headlines. Instead, it was a subtle, almost tentative alteration, like a candle flame wavering in a room with no draft. Astronomers started to observe that this specific star, Betelgeuse, was gradually fading. The dimming was slow at first, but then it became undeniable. A giant star, one of the most brilliant in our sky, was losing so much of its light that people could see the difference with their own eyes from their own backyards. This was profoundly strange, as stars, particularly those observed for centuries, are not supposed to change so noticeably without a clear explanation. So tonight, we will delve into that mystery together. We will proceed slowly, moving step by step through the nature of Betelgeuse, what occurred, the initial theories from scientists, and why, even today, some questions remain without definitive answers. But before we venture too deep into the cosmos, let me ask you a simple question. Where are you right now as you listen? Perhaps you are at home, comfortable in a blanket, with the room lit only by a single soft lamp. You might be in bed, allowing the events of the day to quietly recede. Or maybe you find yourself in a more unexpected setting, on a train, in a still office, or even gazing at the stars through a window. And if you happen to be aware of the time, perhaps it is late evening, or one of those quiet hours when the world seems to pause, as if holding its breath. It is a gentle thing to consider, isn't it? That as we are here together, listening and wondering, the light from Betelgeuse continues its journey across space. It is still traversing the silent darkness, finally arriving here after traveling for hundreds of years. The light that reaches you this evening departed from that star long before any of us existed, before the modern inventions we rely on, and before entire generations came and went. If you find these unhurried explorations of science to be a source of calm, or simply a pleasant way to unwind your thoughts, I would be very grateful if you would like the video, subscribe, or share it with someone else who might appreciate drifting through the cosmos at this gentle rhythm. Your support helps this quiet endeavor find more people who could use a moment of peace at the end of their day. Now, let us properly begin our story. Betelgeuse has always been a remarkably easy star to locate. Even those with very little astronomical knowledge can typically identify Orion thanks to the 3 stars of its belt that form a distinct, straight line. Just above that line is a reddish point of light, a bit brighter and warmer in tone than the stars surrounding it. That is Betelgeuse. For the vast majority of human history, it was merely part of the celestial scenery, as reliable as the phases of the moon or the daily sunrise. Ancient cultures across the world gave it names, wove it into their myths, and used its position to navigate. Sailors crossing dark oceans would have looked to it for guidance. Farmers waking before the sun would have seen its light. Children lying in open fields would have gazed up at it, completely unaware they were looking at a star of such immense scale. If Betelgeuse were placed where our sun is, its outer edge would extend beyond the orbit of Mars, and perhaps even graze the path of Jupiter. That is the first truly astonishing fact about this star. Its size is enormous, beyond our everyday comprehension. Our own sun, which already seems vast next to Earth, would appear like a tiny marble in comparison. And yet, for all its great volume, Betelgeuse is not exceptionally massive when compared to certain other stars. It is swollen and expanded, puffed out into a state that astronomers call a red supergiant, a phase that marks the later stages of a star's existence. In this phase, the star's outer layers grow and cool, which produces its characteristic reddish glow, much like the embers of a fire that is no longer burning fiercely, but still radiates warmth. For a very long time, scientists had a solid understanding of this general picture. Betelgeuse was old, at least in stellar terms, and it was approaching the end of its life cycle. Someday, likely tens of thousands of years from now, it was expected to explode as a supernova, for a short time outshining its entire home galaxy. But according to all reasonable calculations, that day was not supposed to arrive anytime soon. This is what made the events of recent years so captivating. Sometime around late 2019 and into early 2020, observers started to detect something highly unusual. Betelgeuse was losing its brightness. This was not a minor dip or one of the subtle fluctuations often seen in variable stars. It was a significant drop. The star dimmed to approximately 1/3 of its normal luminosity, becoming visibly fainter than nearby stars it typically surpassed in brilliance. Astronomers, both professional and amateur, began to carefully document the change. Telescopes all over the planet were directed toward Orion. A steady stream of data began to pour in, and the numbers confirmed what was plain to see. This was no illusion. Betelgeuse was genuinely fading. Initially, the mood was one of excitement tinged with a bit of apprehension. When a red supergiant behaves erratically, one potential reason is that it is entering the final stages before a supernova. The very notion of a star exploding in our cosmic vicinity, bright enough to be seen in daylight, quickly seized the public's imagination. Headlines started to surface, and people began to ask if Betelgeuse was on the verge of exploding. Speculation filled social media, with some envisioning a brilliant second sun in the sky. Others worried more anxiously about whether such an event could have any effect on Earth. Scientists, however, had a much more measured response. While a Betelgeuse supernova would certainly be a breathtaking spectacle, the star is about 600 light-years away, far too distant to pose any threat to our planet. The light would be intense, yes, but ultimately harmless, like a faraway lighthouse beam shining across a vast ocean. Nevertheless, the central question lingered. Why was the star dimming? A curious reality of astronomy is that resolving the surfaces of faraway stars remains a profound challenge, even for our largest and most advanced telescopes. The overwhelming majority of stars register as simple points of light, even when viewed through instruments powerful enough to resolve entire galaxies millions of light-years in the distance. Betelgeuse, however, presents a rare exception due to its immense size and relative closeness, which has allowed astronomers to capture actual images of its disk, revealing a glowing, somewhat non-uniform surface. When scientists analyzed images taken before the Great Dimming against those captured during it, they observed something quite unexpected. A substantial portion of the star was noticeably darker than the rest, giving the impression that a vast shadow had been cast across its face. This finding pointed towards several intricate potential explanations. One hypothesis was that Betelgeuse had expelled a tremendous cloud of gas and dust, which then cooled and condensed into particles that obstructed a portion of the star's light from our perspective. One might visualize a lantern veiled by drifting smoke. While the lantern itself continues to burn brightly, the intervening smoke reduces its apparent glow from certain vantage points. Another line of reasoning centered on the stellar surface itself. Red supergiants are not the serene, smooth spheres one might imagine. Instead, their surfaces boil and churn with gigantic convection currents, any one of which is larger than the orbit of Earth. These rising and falling zones of hot gas generate a shifting mosaic of bright and dark patches that evolve slowly over time. If a single one of these darker areas were to grow to a sufficient size, it could feasibly diminish the star's apparent brightness, at least for a while. As more information was gathered, the evidence began to favor a synthesis of both these effects. The most likely scenario is that Betelgeuse experienced a massive ejection of material that subsequently cooled to form dust, all while its inherently turbulent surface continued its own rhythm of pulsing and shifting. Yet even with these plausible explanations, the timing and magnitude of the event retain a sense of mystery. The dimming was more profound than what most scientists would anticipate from the star's normal fluctuations. While not completely without precedent, it was certainly strange enough to trigger intensive investigation. And here, the narrative deepens, because Betelgeuse is not merely brightening and fading in predictable cycles. It is a star navigating a deeply unstable phase of its existence, shedding mass, pulsating, and evolving in ways that defy precise, detailed prediction. Stars of Betelgeuse's type live their lives at an accelerated pace compared to smaller stars like our Sun. They consume their nuclear fuel with incredible speed, altering their structure over what are, in astronomical terms, very short periods. Deep within the star, successive layers fuse progressively heavier elements, creating an onion-like interior of distinct fusion zones, each contributing to its energy output in a slightly different manner. These internal processes have a direct impact on the outer layers, prompting the star to expand, contract, and occasionally cast off enormous shells of gas into the surrounding space. Over eons, Betelgeuse has enveloped itself in a complex environment of its own previously ejected matter, a sort of slow-motion nebula of its own creation. When new outbursts happen, they must interact with this older material, generating complex patterns that are difficult to decipher from such a great distance. Therefore, when Betelgeuse faded, astronomers were not just observing an isolated incident. They were glimpsing a single chapter in a long and elaborate story, one that has been developing for millennia and will persist for thousands of years more. Even today, while the star has regained a portion of its luminosity, it has not reverted to its prior state of behavior. Its cycles of brightening and dimming appear to have been subtly changed. Its surface continues to exhibit transformations. Observatories around the world maintain their vigil, collecting data night after night, seeking to understand what these variations signify about the final stages of massive stellar lives. This reveals the deeper importance of Betelgeuse. It is more than just a celestial point of interest. It serves as one of our premier laboratories for investigating how the most massive stars conclude their existence. This knowledge is vital because supernovae are among the most consequential events in the cosmos. They are responsible for forging many of the heavy elements that constitute planets, oceans, and even the iron flowing through our veins. Long before our Earth was formed, ancient stars exploded and scattered these elements across space, seeding the cosmic clouds from which our solar system would eventually coalesce. In a very tangible way, to understand stars like Betelgeuse is to better understand our own origins. There is a certain reassurance in the night sky, especially for those who observe it regularly. Patterns tend to repeat. The constellations make their seasonal return. The stars maintain their positions night after night and year after year, as if in a silent agreement to remain still for our recognition. Even the planets, for all their wandering, trace predictable courses once their movements are understood. Astronomers, and indeed much of science, rely on this dependability. When celestial objects behave consistently over long stretches of time, patterns can be identified, and from those patterns comes understanding. This is precisely why Betelgeuse commanded such widespread attention when its behavior began to deviate. For the majority of recorded history, Betelgeuse had been stable in the way a red supergiant is expected to be. This is not to say it was unchanging. In fact, Betelgeuse has always been classified by astronomers as a variable star, which means its brightness naturally ebbs and flows over time. However, these fluctuations had always followed a familiar and well-documented rhythm, with cycles that could be tracked and anticipated. It was akin to hearing a familiar piece of music. The notes might rise and fall, but the core melody was always recognizable. Then, in late 2019, that melody shifted. Observers who systematically track the brightness of stars began to note that Betelgeuse was fainter than usual. Initially, the change was subtle enough to be considered part of its ordinary cycle, but the dimming persisted, and night after night, new measurements confirmed the same downward trend. The star was fading more than anyone had foreseen. Astronomy is a discipline built on a long tradition of careful patience. Scientists are not prone to making hasty judgments. Instruments can malfunction, and atmospheric conditions can skew observations. Any data must be corroborated by multiple independent sources before anyone dares to suggest something truly unusual is occurring. Consequently, telescopes across the globe were directed toward the constellation Orion. Observatories shared and compared their readings. Amateur astronomers, many using equipment in their own backyards, also contributed their valuable observations. One of the quiet virtues of astronomy is that many breakthroughs arise not from singular, dramatic moments, but from the steady accumulation of meticulous watching. The data was in agreement. Betelgeuse was indeed dimming, and it was doing so rapidly. By the start of 2020, The star's luminosity had fallen to approximately 1/3 of its typical brightness. To offer some perspective, one might picture a great coastal beacon, a light that had shone for generations, which then began to fade until it was only a ghost of itself in the fog. It was not gone, nor was it extinguished, but it had clearly undergone a change that commanded notice. The fabric of the night sky itself felt subtly rewoven. Individuals familiar with the constellation Orion could perceive this alteration without any special equipment. The shoulder of the Great Hunter simply did not possess its former brilliance. This was no longer a phenomenon confined to specialists. The story soon migrated from astronomical observatories into the sphere of public discourse. In newspapers and science publications, the same essential question began to appear, phrased in various ways. Was Betelgeuse on the verge of exploding? It is not difficult to see why this inquiry arose with such speed. Red supergiants are known to conclude their existence in supernova explosions. Such events rank among the most energetic occurrences in the cosmos, briefly unleashing more light than is produced by entire galaxies. Furthermore, in astronomical terms, Betelgeuse is situated relatively near to Earth. If an explosion of this magnitude were to happen, it would be plainly visible during the day. For a period of weeks, or perhaps even months, a brilliant new light would appear in the heavens, one that could rival the luminosity of the full moon. That prospect alone was powerful enough to seize the imagination of people across the globe. Among professional astronomers, however, the atmosphere was more considered. It was not one of disinterest or dismissal, but of caution. While it is true that Betelgeuse is approaching the end of its life, the term approaching can be deceptive when discussing stars. Approaching the end might still translate to tens of thousands of years. On a cosmic scale, this is but a moment. On a human scale, it is an era longer than all of recorded history. So, scientists started to pose a more precise question. The query was not whether it was about to explode, but what precisely was happening to it in the present. To find an answer, they first had to understand the star's normal behavior. Betelgeuse is not a placid star. Its surface is a turbulent and irregular place, sculpted by immense currents of rising and falling gas. Unlike our own Sun, which features many comparatively small convection cells across its surface, Betelgeuse may possess only a handful. Yet, each one can be so vast it could easily encompass the entire orbit of Earth. These massive currents carry hot plasma upward while allowing cooler material to descend. This entire process results in natural variations in the star's brightness, creating cycles that have been studied by astronomers for decades. Some of these cycles span a few hundred days, others can last for several years. But the pronounced dimming of 2019 and 2020 did not conform to the pattern of any established cycle. That was the first clear signal that something new was taking place. An additional clue emerged from spectroscopy, which is the analysis of light separated into its component wavelengths. By studying the spectrum of Betelgeuse, astronomers were able to ascertain the temperature of its surface and the makeup of the material around it. What they discovered was intriguing. The star's surface temperature had not fallen nearly enough to explain such a drastic fading. This implied that the star itself was still generating almost the same amount of light as it had before. Something else had to be obstructing or scattering that light on its journey to Earth. This reasoning led to one of the most persuasive hypotheses: dust. Stars of Betelgeuse's type are known for losing mass. Their outer atmospheres are held only weakly by gravity, and powerful currents can eject matter far out into space. As this material cools, it can condense into tiny particles of dust, with a composition similar to soot or sand, but dispersed over immense volumes of space. If a large cloud of this dust had drifted into the line of sight between Betelgeuse and us, it could account for the reduced brightness without any fundamental change in the star itself. The theory was plausible, but substantiating it would demand more than just speculation. Instruments with the power to directly image the surface of Betelgeuse started to yield critical evidence. The European Southern Observatory's Very Large Telescope, employing a method known as interferometry, captured images that revealed one part of the star's disk was darker than the rest. The dimming was not uniform, but patchy, as if a great shroud had been partially drawn over one side. This observation suggested that a combination of factors might be responsible. There were likely changes on the star's surface, coupled with the presence of dust in its immediate vicinity. Even with this insight, there was still something strange about the timing. Betelgeuse had ejected matter before. It had waxed and waned in brightness before. This particular event, however, felt larger, more sudden, and more extreme than the majority of its known fluctuations. And that observation gave rise to a deeper question. Was this just an extreme manifestation of ordinary behavior for a red supergiant? Or was it perhaps an indicator of something more consequential occurring within the star itself? To appreciate why this question is so important, it is helpful to think about what is happening deep inside Betelgeuse, far beneath the surface that our telescopes can see. At its very center, nuclear fusion is ongoing, but not in the straightforward manner of a star like our Sun. The Sun fuses hydrogen into helium, a stable process that can persist for billions of years. Betelgeuse, by contrast, has already used up the hydrogen fuel in its core. It has progressed to fusing heavier elements within a series of concentric shells, with each layer burning a different type of fuel. This onion-like structure is fundamentally unstable. Each stage of fusion releases energy at a different rate, making the balance between gravity and outward pressure increasingly precarious. The outer layers of the star react to these internal shifts by expanding, contracting, and occasionally erupting. It is a highly complex and dynamic system, where minor changes in the star's depths can produce enormous effects at the surface. This complexity makes prediction extraordinarily difficult. Astronomers can create models for the general behavior of red supergiants, but the specific details are often governed by turbulent processes that are notoriously hard to calculate with precision. So when Betelgeuse dimmed so remarkably, scientists were witnessing a phenomenon that did not fit cleanly into their existing models. It was not entirely unexpected, but neither was it fully explained. For the researchers, this was not a reason for alarm, it was an opportunity. This is because rare events, particularly in stars close enough for detailed study, offer invaluable data. Every measurement collected during the dimming event added another piece to the puzzle, which helps researchers refine their models of how massive stars evolve and shed material during their final phases. All the while, the star itself continued its gradual transformations. By the middle of 2020, Betelgeuse started to brighten once more. Slowly, almost tentatively, it began its return toward its previous luminosity. The dramatic fading that had garnered so much global attention began to subside, and the shoulder of Orion started to recover some of its familiar radiance. But the story was not over. Subsequent observations revealed that the star's behavior had not entirely returned to its previous state. The familiar cycles of its variation seemed subtly changed. New fluctuations, though minor, were now detectable in the data. It was as though the star had found a new equilibrium, a rhythm that was similar to its old one, but not identical. This persistent irregularity hinted that the Great Dimming was more than just a momentary event. It might have been a symptom of a much larger transformation taking place in the star's outer layers, or perhaps even in the deeper processes of its interior. That very possibility is what continues to captivate the attention of astronomers. Betelgeuse, after all, is no ordinary star. It is one of a handful of red supergiants, situated close enough for us to study in extraordinary detail. Each unusual shift it undergoes offers a rare glimpse into a phase of stellar evolution that is typically impossible to observe directly. Most stars that end their lives in a supernova are simply too far away for any detailed surveillance before the final explosion. By the time their light arrives at Earth, the cataclysm is long over, and scientists are left to piece together the sequence of events from the resulting aftermath. Betelgeuse provides something profoundly different, a chance to witness a massive star in its final acts, in real time, as it sheds its material, pulsates, and evolves. This is why even a temporary fading event becomes so significant. The focus isn't merely on its brightness, it's on deciphering the fundamental processes that govern the lives and deaths of stars many times more massive than our own Sun. Yet, there is another layer to this story, one that can be easily missed when concentrating on charts and theories. Betelgeuse serves as a powerful reminder that the cosmos is not a static backdrop. Even celestial objects that appear eternal and unchanging are in constant motion, evolving on timescales that are vast compared to a human life, but fleeting in the grand sweep of cosmic history. The stars we observe tonight are not precisely the same as they were a millennium ago, nor will they be exactly the same a millennium from now. Change is a universal constant, even in the heavens. And in the case of Betelgeuse, that change has become apparent within the span of a single human lifetime, a quiet and remarkable occurrence. There is something deeply humbling in this realization. A star that has shone for millions of years, an object so immense that it would completely envelop the inner planets of our solar system, can still present us with surprises. It can still act in ways that challenge our models and our understanding. In its own slow, distant manner, it defied our expectations of how it should behave. Perhaps that is precisely what makes it such a compelling subject to watch. As astronomers continue their observations of Betelgeuse, carefully measuring its luminosity, mapping its turbulent surface, and tracking the vast clouds of matter drifting away from it, they are doing more than studying a single star. They are gathering clues about the forces that build galaxies, the origins of the chemical elements, and the very processes that ultimately allow for the formation of planets and the possibility of life. Long before the invention of telescopes, and long before anyone knew what stars truly were, ancient observers noticed that one of the lights in the constellation of Orion looked different from the others. While most stars gleam with a sharp, white or bluish light, this particular one had a distinct reddish hue, reminiscent of a distant ember glowing in a dark space. The effect was subtle, but once seen, it was unmistakable. That reddish star, marking the shoulder of the celestial hunter, is Betelgeuse. If you have ever looked up on a clear winter night toward Orion, you may have seen it yourself, without ever knowing just how exceptional it is. The constellation is easy to find. 3 brilliant stars in a straight line form the hunter's belt, and just above them, slightly to the left, is the warm glow of Betelgeuse. Even from brightly lit cities or through a thin veil of clouds, it is often prominent enough to draw the eye naturally. For the vast majority of human history, this was all that could be known about it, a point of reddish light, a steady and familiar part of the sky's nightly pageant. But as astronomy emerged as a formal science, and as instruments grew powerful enough to measure cosmic distances and brightness with precision, Betelgeuse began to reveal its true character. What astronomers discovered was, at first, almost beyond belief. Betelgeuse is not simply a large star, it is enormous on a scale that defies ordinary comprehension. Our own Sun, which feels immense compared to Earth, measures about 1.4 million kilometers in diameter, a number that is itself difficult to visualize. If our planet were the size of a small marble, the Sun would be comparable to a large exercise ball. Betelgeuse, in contrast, is hundreds of times larger than the Sun in diameter. Precise estimates can vary, as the outer layers of a red supergiant lack a well-defined edge. However, if you were to place Betelgeuse at the center of our solar system, its surface would stretch out beyond the orbit of Mars, and depending on the measurement of its atmosphere at any given time, it could even approach the orbit of Jupiter. Imagine gazing up into a sky where the star that replaced our Sun was so vast that the inner planets would cease to exist. Mercury and Venus would be vaporized inside it. Earth's own orbit would be deep within its searing outer layers, submerged in hot, luminous gas. This is the scale of the object we are considering, and yet, for all its colossal size, Betelgeuse is not exceptionally heavy when compared to other massive stars. It is believed to have started its life with approximately 15 to 20 times the mass of the Sun, which is substantial, but not at the extreme end of the stellar scale. What makes it so vast is the tremendous expansion it has undergone with age, swelling outward to become a red supergiant. Most of a star's life is spent in a stable phase, fusing hydrogen into helium within its core. During this period, an equilibrium exists between the inward crush of gravity and the outward push of nuclear fusion. Our Sun is currently in this stage and will remain so for billions of years. Massive stars, however, consume their fuel at a much faster rate. Their cores are hotter, their reactions more rapid, and their lifespans consequently much shorter. When the hydrogen in the core is depleted, the star's entire structure undergoes a dramatic shift. The core contracts and heats up even more, while the outer layers expand and cool. This is the process that creates a red supergiant. Its surface temperature drops enough for it to glow with a reddish light instead of white or blue. But because the star is so incredibly large, its total energy output remains immense. Even a relatively cool surface can radiate a staggering amount of light when it has that much area. Betelgeuse shines with the luminosity of tens of thousands of suns, making it one of the most prominent stars in the night sky, despite being hundreds of light years away. In another sense, however, Betelgeuse is quite fragile. Its extended outer layers are only weakly held in place by its gravity. The star is so large and its material so diffuse that its surface gravity is extremely faint compared to that of the Sun. To be present somehow in the outer atmosphere of Betelgeuse would be an experience of near-zero gravity, where one could witness enormous currents of gas rising and falling with a majestic slowness, like immense weather systems moving through a glowing, reddish sky. The scale of these currents is difficult to overstate. On our Sun, the convection cells, which are the upward and downward motions of hot plasma, reach sizes comparable to Earth's continents. On Betelgeuse, however, they can be as vast as the orbits of entire planets. One can imagine a single bubble of hot gas, larger than the span between the Sun and the Earth, ascending slowly, cooling, and then sinking back down over the course of months or even years. This is precisely the kind of movement that sculpts the surface of this star. As a result of these gigantic convection cells, the surface of Betelgeuse is not smooth or uniform. Instead, it is a mottled, uneven, and perpetually changing landscape. Bright and dark regions drift gradually across its face, which contributes to the natural fluctuations in brightness that astronomers have noted for decades. In fact, what is remarkable is that Betelgeuse was among the very first stars, aside from our own Sun, whose surface features were ever resolved by telescopes. This distinction alone makes it quite special. The vast majority of stars are simply too far away and appear too small to reveal any detail, even when viewed with our most powerful instruments. Betelgeuse stands as one of the rare exceptions, being close enough and large enough for astronomers to study its surface directly. The matter of its distance is an interesting topic in its own right. Betelgeuse is situated approximately 600 light-years from us, though this figure continues to be refined as our measurement techniques improve. This means the starlight that reaches your eyes on any given night started its journey around the time Galileo first aimed a telescope at the heavens. The star you perceive is not as it exists in this moment, but as it was centuries ago. Of course, this time delay applies to all stars, but it feels more palpable with Betelgeuse because the timescale is long enough to be significant, yet short enough to feel connected to our own human history. When you observe Betelgeuse, you are peering into the past, but it is not a past so ancient as to be unimaginable. It is a past that maintains a quiet link to the world we recognize. Another extraordinary feature of Betelgeuse is the material that surrounds it. Observations made in infrared and radio wavelengths have uncovered immense clouds of gas and dust drifting away from the star, which is clear evidence of continuous mass loss. Betelgeuse is slowly shedding its outer layers, sending steady streams of matter out into the cosmos. Over eons, this expelled material has formed a complex environment around the star, faintly illuminated by its own light. These clouds are carriers of the elements forged within the star, such as carbon and oxygen, enriching the interstellar medium from which new stars and planets will one day be born. In this way, Betelgeuse is not merely a star approaching the conclusion of its life. It is also a source for future beginnings. And yet, despite all this immense activity, from our perspective on Earth, Betelgeuse appears as a serene, steady, reddish point of light rising in the evening sky during the winter months and setting quietly before the dawn. Its true nature is concealed by distance and scale, unveiled only through meticulous measurement and patient observation. Patience is a virtue that astronomers must constantly cultivate. The changes in stars typically unfold over very long periods. Even the most dramatic events can take months or years to become fully apparent. This is why the dimming of Betelgeuse was so arresting. The surprise was not that the star changed, but that the change was visible on a human timescale, becoming noticeable over weeks and months rather than centuries. For a star, this was almost abrupt. It was as if a familiar landmark, one that had stood unaltered for generations, had suddenly changed its appearance. It was not destroyed or gone, but it was different enough for everyone who knew it to take notice. This event is what prompted the world to look at Betelgeuse more closely than ever before. A great number of telescopes turned their focus toward it. Space observatories contributed to the effort, studying the star in wavelengths that are invisible to the human eye. Its light was analyzed by spectrographs. Signals from multiple telescopes were combined by interferometers to achieve resolutions that once seemed impossible. Each new observation added more detail to our understanding of this enormous, restless star. Astronomers were able to measure the motion of gas flowing away from its surface. They tracked the expansion and contraction of its outer layers. They studied the variations in temperature across its visible disk. Bit by bit, they started to assemble a more complete picture of how a red supergiant lives and evolves. But even with this wealth of data, Betelgeuse has remained unpredictable in some respects. While models of stellar evolution can outline general patterns, individual stars often display their own unique characteristics, which are shaped by factors like rotation, internal mixing, magnetic fields, and subtle compositional differences. It seems Betelgeuse is one of those stars whose behavior defies simple classification. Perhaps this is not so surprising. A star of such immense size and complexity cannot be expected to operate like a simple system. Its interior is a layered, turbulent, and constantly shifting environment. It is a vast engine of nuclear reactions and convective motion, operating on scales that challenge both our observational capabilities and our theoretical models. From our distant viewpoint, we can only see the outermost layers, the thin, glowing surface that radiates light into space. What occurs beneath that surface, deep within the core where fusion continues, remains hidden from us, inferred only through models and indirect measurements. Sometimes, however, the surface provides hints that something deeper is changing. This is what made the dimming event so compelling. It was more than just a shift in brightness. It was possibly a sign of processes unfolding deep inside the star, processes that could teach us more about the final stages of a star's life. Betelgeuse is, after all, nearing the end of its existence, not tomorrow and not next year, but on a cosmic timescale, its remaining time is relatively short. One day, it will deplete its nuclear fuel, and the delicate equilibrium holding it together will fail. Its core will collapse inward, rebound, and propel a shockwave outward in one of the universe's most powerful explosions, a supernova. That moment will inevitably arrive. The question is not if, but when. Until that day comes, every fluctuation, every shift in brightness, and every eruption of gas is part of the slow, intricate journey toward that final event. For now, Betelgeuse continues to glow on Orion's shoulder, still visible, still changing, and still offering clues to those who watch with patience. To grasp why the strange behavior of Betelgeuse has commanded so much attention, it is helpful to step back and consider what astronomers normally expect from stars. This understanding is not merely abstract. It is rooted in a comprehensive and well-established pattern that explains how stars are born, the manner in which they live out the majority of their lives, and the processes that lead to their eventual demise. The reason for this is that stars, for all their immense scale and complexity, operate according to a set of rules. While these cosmic laws are not perfectly predictive in every minute detail, they are coherent enough for scientists to outline the typical life path a star is expected to follow. For most of its existence, Betelgeuse has adhered to that path with remarkable fidelity. The story of a star originates not in light, but in darkness. Its genesis is as a small part of a vast, cold cloud of gas and dust that drifts serenely through interstellar space. These formations, known as molecular clouds, can span dozens or even hundreds of light years across. For much of their long lives, they exist in a state of calm, appearing almost static from the perspective of human timescales. Yet gravity is a persistent force, constantly at work even in the most frigid and rarefied corners of the cosmos. Over eons, minor fluctuations in density cause certain regions within the cloud to begin a slow process of inward collapse. The material accumulates gradually at first, but the pace quickens as the gravitational pull intensifies. Gas and dust fall inward, becoming compressed and heated, eventually forming a dense, embryonic object called a protostar. At this point in its development, the object is not yet considered a true star. While it emits a faint glow generated by the heat of its own compression, the critical process of nuclear fusion has not yet ignited within its core. Reaching that milestone requires temperatures and pressures of an extraordinary magnitude, far greater than what can be achieved through simple gravitational heating. As more and more material accretes onto the protostar, the core temperature climbs into the millions of degrees. Finally, a crucial threshold is crossed. The nuclei of hydrogen atoms begin to fuse together to form helium, a reaction that unleashes a tremendous amount of energy as light and heat. In that very moment, a star is truly born. The energy now being generated by fusion creates an outward pressure that counteracts the relentless inward pull of gravity. This delicate equilibrium is the key to a star's stability. Gravity works to crush the star inward, while the energy from fusion provides an opposing outward force. So long as these two fundamental forces remain in balance, the star will shine with a steady light. This phase of stellar life, known as the main sequence, is by far the longest portion of its existence. Our own Sun is currently in this stage and has been for approximately 4.5 billion years. It is expected to remain there for another 5 billion years before it begins to undergo significant changes. However, not all stars evolve at the same tempo. The most massive stars, those containing many times the mass of the Sun, burn through their available fuel with astonishing speed. Their cores are significantly hotter, their fusion reactions proceed at a much faster rate, and as a result, their lifespans are dramatically shorter. A star with the mass of Betelgeuse might only live for about 10 million years from its birth to its death. While that sounds like an immense stretch of time, it is merely a brief flicker when compared to the Sun's total expected lifetime of around 10 billion years. An effective way to visualize this difference is to think of two candles. One is slender and has a small, slow-burning flame that can last for an entire evening. The other is thick and wide, producing a brilliant, intense flame that consumes all its wax in just a fraction of that time. Massive stars are very much like that second candle. They are exceptionally brilliant, but their lives are fleeting. Eventually, the supply of hydrogen in the star's core is exhausted. As fusion slows, the carefully maintained balance between gravity and outward pressure begins to falter. Gravity starts to gain the advantage, causing the core to contract under its own immense weight. As the core shrinks, it heats up once again, and in response, the star's outer layers begin to expand outward. This marks the beginning of the star's giant phase. For stars with a mass similar to our Sun, this process leads to the formation of a red giant. For much more massive stars, such as Betelgeuse, the expansion is far more profound, producing a red supergiant, which is among the very largest types of stars in the universe. During this stage, the core becomes hot enough to initiate the fusion of helium into heavier elements, primarily carbon and oxygen. Later, if the star is sufficiently massive, the fusion process can continue, creating elements like neon, magnesium, silicon, and ultimately, iron. This results in a layered structure that is sometimes compared to an onion, with different shells fusing different elements at various depths. Each of these fusion layers contributes to the star's total energy output, but the entire system becomes progressively more complex and unstable as heavier elements are forged. The element iron, in particular, signifies a crucial turning point. The fusion of all elements lighter than iron results in a net release of energy, which helps to support the star against gravitational collapse. Fusing iron, however, consumes energy rather than producing it. Once the core of a star becomes predominantly composed of iron, the process of fusion can no longer generate the pressure required to counteract gravity. At this juncture, the end arrives with incredible swiftness, at least on a stellar timescale. The core collapses in a fraction of a second, imploding inward at a tremendous velocity. When this collapse is abruptly halted, the resulting rebound propels a powerful shockwave outward through the star's remaining layers, violently tearing the star apart in a supernova explosion. This cataclysmic event can, for a brief period, outshine an entire galaxy. It also serves a vital cosmic purpose by scattering heavy elements far into space, enriching the interstellar medium, and providing the raw materials for the formation of future stars, planets, and ultimately, life itself. This general sequence, from a birth in a molecular cloud to a final, explosive death in a supernova, is the established life cycle for a massive star. For a very long time, Betelgeuse seemed to be following this exact script. Astronomers were able to estimate its mass, its temperature, and its current evolutionary stage with confidence. The models indicated that it had already used up the hydrogen in its core and was now in the process of fusing heavier elements in shells surrounding a contracting center. Its immense size and distinct reddish hue were a perfect match for the theoretical profile of a red supergiant nearing the end of its life. In broad strokes, nothing about Betelgeuse appeared out of the ordinary. And yet, even within this predictable framework, there is always room for individual variation. Stars are not all identical. Differences in their rate of rotation, their initial chemical composition, and the efficiency of internal mixing can subtly alter the details of their evolution. Some stars lose mass at a faster rate than others. Some exhibit more pronounced pulsations. Others develop complex magnetic fields that can influence the movement of material in their outer layers. As astronomers have come to understand, Betelgeuse is one of the more restless examples of its kind. Its outer layers are only loosely bound by gravity, and it sheds material into the surrounding space at a remarkable rate. Great streams of gas flow outward from the star, forming vast clouds that slowly drift away. Over time, these expelled clouds accumulate, creating a complex and layered environment around the star itself. Concurrently, the star is known to expand and contract in rhythmic cycles. These pulsations are capable of changing its brightness by noticeable amounts, even under what are considered normal conditions. For decades, observers have carefully tracked these fluctuations, identifying distinct patterns that repeat over periods of hundreds of days. Therefore, the fact that Betelgeuse is a variable star was not in itself surprising. What was truly astonishing was the sheer scale and suddenness of the dimming event that commenced in 2019. To grasp why this was so significant, it is useful to consider just how predictable most stars are. The Sun, for example, varies in its brightness by only a minuscule fraction over the course of its one-year activity cycle. A great number of variable stars exhibit predictable, recurring cycles, ones that can be charted with remarkable mathematical accuracy. Betelgeuse, however, appeared to deviate from its established cadence. The star's luminosity fell much further than anticipated, and the event's timing failed to align with any of its recognized cycles. It was akin to a dependable timepiece, after years of steady function, suddenly losing its measure. This deviation from the norm raised the compelling question of whether something beyond ordinary pulsation was occurring. One of the prominent explanations, as has been considered, was centered on the formation of dust. If the star had ejected a significant quantity of matter, which then cooled into dust particles, this cloud could have concealed some of the light traveling toward Earth. In such a scenario, the dimming would not signify a decrease in the star's actual energy production, but would instead be the result of a transient shroud positioned between the star and our vantage point. An alternative theory pointed to transformations on the star's surface related to its temperature or its physical structure. Enormous convection cells might have generated vast, cooler areas, thereby diminishing the star's apparent brightness as seen from our perspective. Both of these explanations are consistent with the accepted framework for how red supergiants are expected to behave. What made the Betelgeuse event so captivating for study, however, was the seemingly unprecedented intensity of the effects. And this is because, while scientists have a solid grasp of the general arc of stellar evolution, the specific mechanisms at play during the final phases of a massive star's life are not as well understood. Observing stars like Betelgeuse presents a precious chance to validate theoretical models with real-world data. Simulating a red supergiant within a computer is one challenge. Witnessing one in the celestial theater as it transforms in real time is an entirely different matter. The scientific value of Betelgeuse is also greatly enhanced by its relative closeness. A great many red supergiants are situated thousands, or even tens of thousands, of light years from us, which complicates any attempt at detailed observation. At a distance of approximately 600 light years, Betelgeuse is near enough for its surface to be examined directly using sophisticated instruments. This proximity allows astronomers to map temperature differences, observe the motion of gases, and even witness the formation of dust clouds with unparalleled clarity. Every one of these observations adds to a more complete picture of how these colossal stars shed mass, how their outer atmospheres function, and how they ultimately detonate. And still, for all of this accumulated knowledge, profound uncertainties remain. For instance, forecasting the precise moment a red supergiant will go supernova is exceptionally challenging. The concluding stages of a star's existence can unfold with surprising speed, yet the timescales are still immense when compared to a human life. A star might seem perfectly stable for centuries, only to undergo a profound change in just a few years. The recent behavior of Betelgeuse is not a definitive signal of an impending supernova, but it serves as a powerful reminder that these stars are dynamic, evolving entities, not static points of light. It also calls to mind something quieter, though no less significant. The universe is in a constant state of flux. Even the stars, once symbols of the eternal and unchanging, are participants in a grand cycle of creation, existence, and dissolution. The very elements that compose our world and our bodies were forged inside ancient stars that lived and perished long before our own planet came to be. When we gaze at Betelgeuse, we are seeing more than just a faraway object. We are observing a moment in a cosmic process that has been shaping the universe for billions of years. As astronomers persist in their watch over this giant on Orion's shoulder, charting its brightness and analyzing its turbulent surface, their inquiries go beyond the simple question of why it faded. They are probing deeper into how massive stars evolve, how they disperse their mass into space, and how they arrive at their final, spectacular end. For a considerable period, Betelgeuse was a star that observers felt they could count on, not for its constancy, but for the familiar nature of its variations. For more than a century, astronomers had monitored it with care, learning its distinct behaviors over time. Its luminosity would wax and wane through a series of recurring cycles. Some of these periods were brief, others more extended, yet they all conformed to patterns that could be charted and forecasted with a fair degree of precision. This sort of long-term familiarity fosters a quiet sense of assurance. When an astronomical object operates within established parameters for year after year, there is a natural expectation among observers that its rhythm will persist. So, when Betelgeuse started to stray beyond these familiar boundaries, the initial response was not one of alarm, it was one of scientific curiosity, followed by meticulous verification. The narrative of this event doesn't open with a startling proclamation, but with small, methodical measurements. Sometime in late 2019, astronomers dedicated to monitoring variable stars began to register that Betelgeuse seemed a bit fainter than it should have been for that particular point in its cycle. At first, the change was not especially pronounced, merely a fraction of a magnitude, a variation that could plausibly be attributed to normal pulsations or minor surface phenomena. Nevertheless, the data points were recorded. Observers documented the numbers, checked them against historical records, and waited to see what would develop. As days turned into weeks, the star's brightness kept falling. This was strange enough to warrant much closer scrutiny. Betelgeuse was known for its variability, but this particular decline seemed more precipitous than usual. Observatories that maintained regular logs of the star started to take their measurements more frequently. Amateur astronomers, a community that provides invaluable data to organizations like the American Association of Variable Star Observers, also began to submit their findings. One of the truly remarkable qualities of modern astronomy is its collaborative spirit. While professional telescopes offer data of the highest precision, a worldwide network of devoted observers can track stars on a nightly basis, compiling exhaustive records that can span many decades. As these reports began to build up, a distinct trend became undeniable. Betelgeuse was not just experiencing a minor dip in brightness, it was fading at a pace that far outstripped its typical fluctuations. At this juncture, the central question evolved. It was no longer about whether this was part of a normal cycle, but rather, what was the underlying cause? By December 2019, the dimming had grown so significant that it was apparent even to the unaided eye. Anyone familiar with the constellation Orion could perceive that the red star marking its shoulder appeared weaker than normal. It no longer held its customary dominant position in the constellation. Other nearby stars seemed to rival it in brightness, an occurrence that would have been highly unusual under normal circumstances. This public visibility gave the event an immediacy that astronomical phenomena often lack. One did not require a telescope or a spectrograph to notice that a change had taken place. A clear night and a few moments of patient observation were all that was needed. The night sky itself had a subtly altered appearance, It was during this time that astronomers also started to examine the star's light with much greater analytical detail. At first, the change in Betelgeuse was a subtle affair, noticed only by the most careful observers. Night after night, scientific measurements began to stray from their familiar patterns. To most people looking toward the constellation Orion, however, everything appeared normal. The hunter's reddish shoulder was still there, a recognizable beacon in the winter sky, but the fading continued, growing more pronounced with each passing week. Spectroscopic analysis of the star's light revealed a curious detail. The surface of Betelgeuse had not cooled enough to account for such a profound loss of brightness. This suggested that the star's total energy output remained largely the same, pointing instead to some external factor interfering with the light on its journey toward Earth. The distinction was a critical one for astronomers. A cooling of the entire stellar body might have signaled fundamental shifts deep within its core, perhaps even processes connected to the final stages of its life. If, however, some form of material was simply obscuring the view from outside the star, the explanation would be entirely different. Further clues emerged from observations across different wavelengths of light. In the infrared spectrum, which is especially sensitive to heat and dust, there were clear indications of a possible cloud of matter enveloping Betelgeuse. Such a cloud would be consistent with the data, as dust grains are known to absorb and scatter visible light, while allowing infrared radiation to pass through more easily. To confirm this theory, though, researchers needed to capture a direct image of the star itself. This presented a significant technical hurdle. From our distant vantage point, even the most colossal stars appear as mere pinpoints, and resolving any surface features requires extraordinarily sophisticated instruments. Using a technique called interferometry, which combines the light from multiple telescopes to achieve incredibly high resolution, astronomers were finally able to create images of Betelgeuse's disk with surprising clarity. A comparison between these new images and earlier ones revealed something striking. A large portion of the star's visible surface now appeared substantially darker, as if a section of it were either cooler or somehow hidden from view. This finding gave weight to a hybrid explanation, one where both changes on the star's surface and a surrounding veil of dust were contributing to the effect. All the while, the great dimming continued. By early 2020, Betelgeuse had faded to its faintest point in more than a century of observation. At its minimum, its luminosity had fallen to just 1/3 of its typical brilliance. For such a prominent star, this change was nothing short of extraordinary. The event soon captured widespread attention, with headlines questioning if Betelgeuse was on the verge of exploding. Social media platforms filled with speculation, as many people imagined the imminent arrival of a supernova that would illuminate the night with a radiance unseen in modern times. The scientific community responded with a more measured and careful perspective. They explained that while a supernova is certainly in Betelgeuse's distant future, there was no evidence to suggest that such a cataclysm was about to happen. The physical processes that lead to a star's final collapse are immensely complex, and a simple drop in brightness is not a definitive signal. In fact, the prevailing view among most scientists was that the dimming was caused by more routine, though still fascinating, phenomena related to surface activity and mass loss. Nevertheless, the timing of the event was intriguing. Betelgeuse is known to be in a late stage of its life. As a red supergiant, it belongs to a class of stars known for their unpredictable and sometimes erratic behavior. Large-scale eruptions, rhythmic pulsations, and periods of enhanced mass loss are all characteristic of this final evolutionary phase. What made this particular event so special was not just its magnitude, but the unique scientific window it opened. It was perhaps the first time in history that astronomers could observe a red supergiant undergoing such a dramatic transformation with a full array of modern instruments, collecting data from multiple observatories across the entire spectrum of light. The experience was akin to watching a familiar landmark on the horizon suddenly shift, revealing details that had always been concealed. Over the following weeks, the star reached its minimum brightness and then slowly began its recovery. The return of its light was a gradual, almost cautious process, as if the star were carefully finding its way back to equilibrium. By the middle of 2020, Betelgeuse had brightened considerably, though it had not yet returned entirely to its previous level of intensity. The immediate sense of crisis, if it could be called that, seemed to have passed. But the episode left behind a wealth of invaluable data and a number of compelling, unanswered questions. What precisely had triggered the massive ejection of material that likely formed the dust cloud? How did the turbulent convection patterns on the star's surface interact with that ejected matter? And were the star's own deep pulsation cycles changing as it continued to evolve? These were not questions with simple answers. Red supergiants are exceptionally complex systems, governed by an intricate dance of turbulent flows, radiation, transport, and nuclear reactions that are notoriously difficult to model with precision. Even so, every new observation helped to refine the overall picture. The emerging consensus was that Betelgeuse had likely expelled a vast quantity of gas from its surface. This gas then cooled and condensed into fine dust particles as it traveled outward into space. This newly formed dust cloud eventually drifted into the direct line of sight between the star and Earth, acting as a screen that partially obscured the star and caused the dramatic dimming. At the same time, it is believed that changes in the star's surface temperature, driven by its enormous convection cells, also contributed to the effect by creating darker, cooler patches that further reduced its apparent brightness. The combination of these factors produced an event that, while rare, was not entirely unprecedented in the life of a red supergiant. Yet, there was something quietly remarkable about witnessing it all unfold in real time. Most of the grand processes of stellar evolution occur on timescales far longer than a human life. Stars are born, evolve, and die over millions or billions of years. Our understanding is typically pieced together by comparing different stars at different stages of their existence, assembling a narrative from individual snapshots rather than watching a single object change continuously. Betelgeuse offered something different, a rare chance to observe change directly, to see a star respond to its own internal and external forces within the span of only a few months. That immediacy gave the event a personal quality that astronomy rarely affords. People could step outside, look up at the familiar shape of Orion, and see a star that had always been a brilliant guidepost now shining faintly. It was as if it were taking a long, slow breath, dimming and then gradually brightening once more. And although the star did not explode, and the sky did not suddenly blaze with the light of a new sun, the episode left a lasting impression on those who followed it. It reminded us that even the most familiar features of the night sky are not fixed. They are dynamic, evolving, and sometimes wonderfully unpredictable. Betelgeuse, in its own silent, majestic way, had blinked. During the latter months of 2019, the light from Betelgeuse began to diminish so consistently that the change became noticeable even to those observing the night sky with the naked eye. A star that had long been one of the two most brilliant points in the constellation Orion was suddenly being matched and then outshone by its normally fainter stellar neighbors. This subtle shift seemed to alter the familiar balance of the constellation's celebrated shape. For anyone who had grown accustomed to the classic outline of Orion, the visual effect was quite striking. We tend to internalize the patterns of constellations almost unconsciously. Once a pattern is recognized, it becomes as familiar as the profile of a local landmark or the distinct silhouette of a tree seen on a daily journey. When one of the primary beacons within that pattern fades significantly, the difference feels instinctual and immediate, even if the reason is not at all clear at first. For their part, professional astronomers were monitoring the quantitative data with a growing sense of fascination. When the star's brightness measurements were plotted on a graph over time, the resulting curve revealed a distinct downward slope, a trend too pronounced to be dismissed as the star's ordinary variability. While Betelgeuse had always been known to fluctuate, this behavior was something different. The drop in its luminosity was more profound and lasted longer than any other such event documented in the entire history of modern astronomical observation. By December, this great dimming had become the central point of conversation for many scientists specializing in the study of massive stars. Observatories began dedicating more of their valuable time to the star, pointing spectrographs in its direction more frequently, and coordinating a broad effort that involved telescopes sensitive to a wide range of wavelengths, from visible light to infrared and radio waves. A remarkable capability of modern astronomy is its power to observe celestial objects across the full electromagnetic spectrum, far beyond the very narrow range of human vision. Observations in the infrared can detect the presence of warm dust or cooler gas, while ultraviolet light can highlight hotter regions, and radio telescopes can trace molecular clouds extending far from the star itself. Each wavelength contributes a unique piece to the overall narrative. As this wealth of multi-wavelength data was gathered, a more detailed picture of the situation started to take shape. It became apparent that Betelgeuse was not just fading uniformly in visible light. The reduction in brightness was more pronounced at some wavelengths than at others, a key finding which suggested that some form of material was selectively blocking or scattering the starlight. This observation pointed toward interstellar dust as a primary candidate for the cause. Dust in space is quite different from the dust found in a home. Its particles are incredibly small, often similar in size to the very wavelengths of light, allowing them to interact with that light in complex and specific ways. Certain wavelengths might be scattered more effectively, while others are absorbed and then re-radiated as heat. And by analyzing these differences across the spectrum, astronomers can deduce the characteristics of a dust cloud, even without directly imaging it. Around this same time, another key piece of evidence surfaced when high-resolution imaging of Betelgeuse's photosphere began showing a notable lack of uniformity. The star did not appear as a consistently bright disk, but instead displayed vast patches that were distinctly dimmer than the rest of its surface. This detail was a critical clue, hinting that the dimming event was not just caused by an intervening cloud of dust, but was also linked to changes occurring on the star's surface, such as enormous convection cells. These massive, churning currents of hot gas can generate cooler areas that emit less light, and if a particularly large cool spot were to grow or rotate into our line of sight, it could account for a drop in the star's overall perceived brightness. Yet even with this potential explanation, the sheer magnitude of the fading remained extraordinary. By the start of 2020, Betelgeuse had dimmed to the faintest level ever documented, at least within the century or so of dependable scientific measurement. At its minimum, the star was shining with less than half of its typical luminosity. A change of this scale was more than just a curious anomaly. It was a major astronomical event. Word of this great dimming soon traveled far beyond the astronomical community. Articles appeared in newspapers and online, television segments discussed the possibility of a nearby supernova, and social media platforms buzzed with images of Orion that contrasted its past and present appearance, making the change in brightness undeniable. For a great number of people, this was the first time they had encountered the concept that stars could visibly change over the course of a single human life. It is natural to perceive the night sky as a constant, an eternal backdrop for the unfolding of human affairs, but the fading of Betelgeuse served as a powerful reminder that the cosmos is a dynamic place, with changes happening on timescales we can personally observe. Throughout this period, scientists were careful to stress that an imminent supernova was not the expected outcome. They explained that the physical processes that precede such a cataclysm are complex, and there were no signs that Betelgeuse's core was experiencing the swift transformations that would signal an impending collapse. Nevertheless, the remote possibility of such an event lent a palpable sense of anticipation to the ongoing observations. If Betelgeuse were to go supernova, it would become the most brilliant such explosion seen from Earth in hundreds of years. The last event of a similar magnitude within our own galaxy took place in 1604, when Johannes Kepler documented a dazzling new star that remained visible for months before it eventually faded from view. Since that time, many supernovae have been seen in distant galaxies, but none have been near enough to approach the spectacular brightness that a Betelgeuse explosion would create. This historical perspective added yet another layer of intrigue to the star's unusual behavior. Even if the dimming proved to be entirely disconnected from an impending explosion, it still presented an unparalleled opportunity to study a red supergiant in extraordinary detail. And so, night after night, the careful observations continued. One of the inherent difficulties in studying Betelgeuse is that it is far from a simple, uniform sphere. Its outer atmosphere is vast and uneven, with enormous plumes of gas that rise and fall across immense distances. The star's luminosity can therefore shift, not just due to internal mechanics, but also because of changes in the vast envelope of material that surrounds it. To separate these complex factors, astronomers employed a suite of complementary methods. Spectroscopy offered data on temperature and movement. Interferometry was used to resolve features on the star's surface, and infrared imaging helped to identify clouds of dust. By cross-referencing these various streams of information, scientists could begin to piece together a coherent model of what was taking place. Over time, a general consensus started to emerge from the research community, centering on the most probable explanation, that Betelgeuse had ejected a substantial amount of its own material, an event likely set in motion by a massive convective upwelling or a powerful pulsation. As this ejected matter traveled outward and cooled, it condensed into a vast cloud of dust, which then drifted into the direct path between the star and observers on Earth. It was also thought that, concurrently, a large, cooler patch had formed on the star's surface, contributing to the overall reduction in its light. The combined effect of these two phenomena, the obscuring dust and the cool spot, was believed to have produced the dramatic fading that had been so carefully recorded. Yet, even with this compelling explanation, certain details of the event still held a degree of uncertainty. What made this event so perplexing was that the sheer quantity of material involved seemed to surpass that of typical mass loss episodes seen in comparable stars. The timing of the fade also failed to align neatly with the star's established pulsation cycles. Furthermore, the dust cloud structure, as inferred from observations, pointed to a complex and asymmetrical form, not a simple, uniform veil of matter. These ambiguities fueled a vibrant discussion throughout the scientific community. New papers were authored, existing models were re-evaluated, and proposals for fresh observations were put forward. All the while, the star itself was beginning its journey back to its former brilliance. By the spring of 2020, measurements confirmed a gradual, yet unmistakable, rise in its luminosity. The recovery was slow, almost tentative, but it was happening. For astronomers who had been tracking the dimming with great focus, this development was both a relief and a source of new questions. It was reassuring because it pointed toward the event being a component of the star's natural variability, rather than a precursor to an imminent collapse. It was also intriguing because the recovery phase offered a wealth of new data, showing how Betelgeuse's atmosphere was responding as the obscuring dust began to dissipate and its surface conditions changed. Even after its brightness had returned to nearly its usual level, scientists continued to monitor the star with exceptional care. The Great Dimming had demonstrated that Betelgeuse could undergo changes that were both swift and profound, and no one wanted to be caught unaware by the next chapter in its story. Indeed, subsequent observations revealed that the star's fundamental behavior had subtly shifted. Its patterns of pulsation seemed to have been altered, with certain cycles growing more prominent while others became less consistent. Whether these were temporary adjustments or signs of a more permanent, long-term evolution remained an open question. What was clear, however, was that Betelgeuse had entered an era of unprecedented scientific focus. An ever-increasing number of telescopes were now trained upon it. More data was being gathered than at any point in the history of astronomy. And a greater number of researchers were dedicating their efforts to deciphering the intricate processes at play within and around this colossal star. Such opportunities are exceptionally rare, as most red supergiants are simply too distant for this level of detailed study. Betelgeuse, by contrast, is near enough that even minor changes in its state can be measured with remarkable precision. Every small fluctuation in its light, every subtle shift in its spectral lines, and every new image of its mottled surface contributes another vital piece to a grand puzzle. That puzzle, in turn, extends far beyond the fate of a single star. A deeper understanding of Betelgeuse's behavior helps astronomers to refine their models of stellar evolution, especially concerning the final stages of massive stars. It allows them to better predict how and when these stars shed their mass, how their atmospheres transform, and what specific conditions might signal an impending supernova. The dimming of Betelgeuse, therefore, was not merely an isolated cosmic curiosity. It served as a direct window into the fundamental processes that govern the chemical evolution of galaxies and nurture the formation of new stars and planetary systems. For those who simply looked up at the clear night sky during the winter of 2019 and 2020, the experience was more direct but just as profound. They witnessed a familiar celestial landmark fade from view, only to slowly reclaim its place. They saw with their own eyes that the heavens are not a static backdrop, but a dynamic stage where change is a constant, even in realms that appear eternal. For many decades leading up to the Great Dimming, Betelgeuse had already been one of the most intensely studied stars in our sky. This was not because it was acting erratically, but precisely because its behavior made it an incredibly useful subject. A red supergiant close enough to be observed in such detail is a rare gift to science. Astronomers had dedicated years to constructing models that could explain how stars of this kind evolve, how they pulsate, and how they lose mass as they approach the end of their lives. Of course, those models did not capture every single detail. Stars are immensely complex systems, and the outer layers of a red supergiant are particularly challenging to simulate accurately. Still, the general expectations were well established. Betelgeuse was expected to vary in brightness, but only within a certain predictable range. It was known to pulse through cycles driven by the expansion and contraction of its vast outer envelope. It was also understood to be steadily losing mass, releasing gas that would cool and drift away into space. All of this was already part of the established picture. So, when the dimming began, astronomers had a solid framework for interpretation. They anticipated seeing variability, and they were not surprised by the idea of dust formation from time to time. What they did not foresee was the sheer scale and the specific timing of the event that unfolded. To appreciate why it was so surprising, it is helpful to examine the patterns that had been recorded before. Betelgeuse is classified by astronomers as a semi-regular variable star. This means its brightness fluctuates over time, but not in the perfectly repeating cycles characteristic of some other pulsating stars. Instead, it exhibits a complex interplay of overlapping rhythms. One of its main cycles has a period of a little over 400 days, which is superimposed on another, longer cycle that spans several years. These variations had been meticulously tracked, and while they were not perfectly predictable, they had always remained within familiar boundaries. In a sense, Betelgeuse had a known personality for observers, not entirely orderly, but far from chaotic. This is precisely why the dimming of 2019 was so conspicuous. When astronomers plotted the star's brightness over time, the sharp decline simply did not fit the established cycles. The dip was deeper than any other in the modern observational record, and it occurred at a moment in the pulsation pattern where such a dramatic drop was not anticipated. That was the first major surprise. Another set of expectations centered on the star's temperature. If a star fades significantly, a plausible explanation is that its surface itself has become cooler. Brightness and temperature are intimately linked. Consequently, astronomers immediately began analyzing the spectral lines in Betelgeuse's light to determine if its surface temperature had changed. What they discovered was unexpected. The temperature had indeed dropped, but only slightly, nowhere near enough to account for the extraordinary loss of brightness. This finding meant that the star was still generating most of its usual energy. The missing light was therefore being blocked or scattered somewhere on its journey from the star's surface to Earth. Dust was the most obvious candidate for this obstruction. Astronomers were already aware that Betelgeuse is enveloped in clouds of material it has shed over eons. Red supergiants lose mass at prodigious rates, and this expelled material often condenses into tiny dust grains as it cools in the vacuum of space. The formation of dust itself, then, was not a shock. The truly surprising elements were the immense quantity of dust that seemed to be involved and the incredible speed at which it appeared to have formed. Existing models of stellar winds and mass loss had suggested that dust creation around Betelgeuse should be a more gradual phenomenon, leading to diffuse clouds that slowly expand over time. What the observations during the dimming revealed, however, was a surprisingly dense cloud that had formed and drifted into the line of sight over a short period. This discovery prompted new questions. What had triggered such a large outflow of material? Why had it occurred at that particular moment? And what could explain the cloud's uneven structure? To seek answers, astronomers turned to high-resolution imaging. Instruments capable of resolving the disk of Betelgeuse provided images showing that the dimming was not uniform across the star's surface. One region appeared significantly darker than the rest. This was another unexpected detail. While large convection cells on red supergiants can produce bright and dark patches, the size and contrast of the dark region observed were larger than most models predicted. It suggested that the processes driving convection in Betelgeuse might be more vigorous or more irregular than previously thought. At the same time, measurements of gas velocities near the star indicated that material had been ejected at speeds consistent with powerful surface activity. This supported the idea that a large plume of gas had risen from the star's surface, cooled, and then condensed into dust. But here again, the scale of the event seemed larger than expected. Astronomers had certainly seen mass loss in red supergiants before. They had observed shells of gas expanding away from other stars, sometimes in dramatic bursts. Yet Betelgeuse's dimming appeared to involve both a significant ejection of material and an unusual pattern of surface cooling, occurring together in a way that was not fully anticipated. Another surprise involved the timescales. In many models, changes in the outer layers of a red supergiant unfold gradually over months or years. The dimming of Betelgeuse, however, developed relatively quickly, becoming dramatic within a matter of weeks. This suggested that the processes driving the change were more dynamic than the models had assumed. It was not that the theories were wrong, they simply lacked the detail needed to predict such events with precision. This kind of realization is common in astronomy. Models describe general behavior very well, but individual objects often reveal complexities that theory has not yet captured. Each unexpected observation becomes an opportunity to refine the models and improve understanding. One of the more subtle surprises involved the star's recovery. Astronomers expected that if dust were the primary cause, brightness would return as the cloud dispersed or moved out of the line of sight. That did happen, but the recovery was not perfectly smooth. The star brightened gradually, with fluctuations that suggested ongoing changes in the surface and surrounding material. Even after the brightness returned to near normal levels, Betelgeuse did not behave exactly as it had before. Some of its pulsation cycles appeared to have shifted, and its overall variability seemed slightly different. This raised the possibility that the dimming event was not just a temporary disturbance, but part of a longer-term evolution in the star's outer layers. That possibility remains an active area of research. Betelgeuse continues to be monitored closely, and astronomers are watching for further changes that might reveal whether the star is entering a new phase of behavior. Another aspect that differed from expectations involved the distribution of dust around the star. Observations in infrared light showed that the material surrounding Betelgeuse was not arranged in neat spherical shells, as some models had suggested. Instead, it formed irregular arcs and clumps shaped by turbulent flows and asymmetric eruptions. This irregular structure makes it more difficult to predict how future outflows will behave. Dust clouds can form in unexpected places, drift in complex patterns, and interact with older material in ways that are challenging to model. In a sense, Betelgeuse turned out to be messier than expected, and that messiness is part of what makes it so valuable to study. Real stars are not perfectly symmetrical spheres. They are dynamic systems shaped by turbulence, rotation, magnetic fields, and the chaotic interplay of gas and radiation. Observing Betelgeuse in such detail has helped astronomers appreciate just how complex the late stages of stellar evolution can be. There was also something else that astronomers had expected but did not see. If Betelgeuse were approaching the final stages before a supernova, certain signs might appear. These could be changes in the core structure that influence the outer layers, shifts in neutrino emission, or other subtle indicators of rapid evolution. None of those signs were detected. This was reassuring, but it also underscored the mystery. The dimming was dramatic enough to attract attention, but not accompanied by the deeper changes that would signal an imminent explosion. In other words, Betelgeuse was behaving in a way that was unusual but not catastrophic, and that left scientists in a position that is both challenging and exciting. They had an event that did not fit neatly into existing expectations, but also did not violate the basic principles of stellar physics. It was a reminder that nature often operates in the spaces between our models, following rules that are more intricate than our simplified descriptions. As more data were analyzed, the picture that emerged was one of a large convective upwelling, possibly combined with a pulsation that lifted a significant amount of material from the star's surface. That material cooled and formed dust, which drifted into the line of sight and caused the dimming. Meanwhile, changes in the star's surface temperature contributed to the effect. This explanation accounted for most of the observations, but not all of them in detail. There were still uncertainties about the exact timing, the amount of material involved, and the processes that triggered the eruption. Those uncertainties continue to motivate new observations and new models. Because Betelgeuse is not just a single object in the sky, It is a natural laboratory for studying how massive stars live and die. Each unexpected behavior provides clues about the physics of convection, mass loss, and the interaction between radiation and dust. And perhaps just as importantly, it reminds us that even in a universe governed by physical laws, there is room for surprise. The stars do not always behave exactly as we expect. Stars operate on their own distinct timelines, their evolution guided by phenomena that may require many years or even entire centuries to fully reveal themselves. With its tremendous scale and perpetually churning surface, Betelgeuse offers a particularly powerful illustration of this reality. The concept that dust might be the agent behind the star's profound fading was already a quiet subject of discussion in observatories and among research teams for several weeks before a wider consensus began to take shape. It was not a particularly dramatic or unconventional line of reasoning. In fact, the idea was grounded in a behavior that is quite typical for stars of Betelgeuse's classification. Red supergiants are known for continuously shedding material from their outer layers, and this matter frequently cools and solidifies into dust. The existence of the process itself was not what was remarkable. The truly surprising element was its apparent magnitude. To appreciate why dust emerged as the most plausible explanation, it is useful to consider the journey of light from a distant star to our planet. As light departs from a star's surface, it propagates through space in straight lines, expanding outward in every direction. If its journey is unobstructed, the brightness we perceive is determined solely by the star's inherent luminosity and its distance from Earth. However, the space between stars is not a perfect vacuum. Clouds of gas and dust can exist between the star and an observer, and even a very fine screen of this dust can cause a significant decrease in brightness. The tiny grains that make up this dust are exceptionally effective at scattering and absorbing visible light, particularly when the size of the particles is similar to the light's wavelength. This means that a comparatively small quantity of dust, if it is concentrated in just the right location, has the ability to make a brilliant star seem considerably dimmer. Astronomers were already aware that Betelgeuse was enveloped by material it had cast off in its past. Previous observations using infrared light had uncovered vast clouds of gas and dust drifting away from the star, creating immense arcs and shells that extended across enormous distances. These structures represented the remnants of earlier instances of mass loss, providing clear evidence that Betelgeuse had been shedding its outer atmosphere for a very long time. Consequently, when the star's light began to wane, it was a logical step to investigate whether a fresh cloud of dust could have materialized and drifted into our direct line of sight. The initial clues that lent support to this hypothesis emerged from measurements taken across different wavelengths of light. While the visible light from Betelgeuse had diminished substantially, its infrared radiation, which is less susceptible to the effects of dust, had not experienced a comparable decline. This specific pattern is precisely what scientists anticipate when a cloud of dust is present. The dust serves to obstruct or deflect visible light, yet it permits a greater amount of infrared radiation to penetrate through. The effect was analogous to viewing a distant lamp through a patch of fog. The lamp's visible brightness is reduced, but the heat it emits can still be sensed. This observation gave considerable weight to the dust theory, though it didn't immediately clarify how such a dense cloud could have formed so rapidly. Dust does not simply materialize from nothing. It is created when hot gas cools and condenses, a process that allows individual atoms to link together and form tiny solid particles. In the vicinity of a star like Betelgeuse, this typically occurs when material is propelled away from the intensely hot surface and transported to cooler regions farther out. In these colder zones, molecules can assemble, and eventually, microscopic grains of dust can begin to accumulate. For this mechanism to generate a cloud thick enough to obscure a star so profoundly, a very large volume of gas would need to be ejected over a relatively brief span. This implied that some form of powerful, energetic event had recently transpired on the star's surface. Researchers then started to explore the potential mechanisms for such a massive eruption. The surface of Betelgeuse is anything but tranquil. It is dominated by enormous convection cells, each one larger than the entire orbit of Earth, which churn hot gas upward from the interior while allowing cooler gas to descend. These massive currents can generate potent upwellings, areas where material surges upward at high speed and can be thrust beyond the star's outer atmosphere. If one of these upwelling events were unusually forceful, it could launch a substantial plume of gas deep into space. As this ejected gas subsequently expanded and cooled, dust could then start to coalesce within it. Before long, observations furnished proof that precisely such an event had occurred. Spectroscopic analysis revealed the telltale signatures of gas moving away from the star, while high-resolution imaging captured irregular features in the material surrounding Betelgeuse. The picture that emerged was one where the star had released a massive cloud of gas, which then condensed into dust and drifted directly into the path of light traveling toward Earth. This explanation successfully addressed many of the observed phenomena, but it also introduced new complexities. One of the remaining puzzles was related to the specific character of the dimming event. Had the dust cloud been spread evenly around the star, the brightness would have faded in a uniform manner. Instead, images revealed that a particular portion of the star seemed darker than the others, which suggested the dust was clustered in one specific area rather than forming a complete, symmetrical shell. This finding pointed to an asymmetric ejection of matter, possibly originating from a distinct region on the star's surface, where convection or pulsation was particularly vigorous. Another unresolved issue centered on the timing. The dimming transpired over a fairly short timescale, indicating that the obscuring cloud must have formed and moved into position very quickly. Standard models of stellar winds generally presuppose much more gradual outflows of material. This forced astronomers to contemplate the possibility that Betelgeuse might undergo episodic eruptions, which are brief but intense events that expel large quantities of matter all at once. Such outbursts are not unknown in the cosmos, but the processes that drive them remain poorly understood. The outer layers of red supergiants are known to be turbulent and unstable, making it exceedingly difficult to predict exactly when and where a large plume of gas might form. In this way, Betelgeuse was presenting a rare and valuable opportunity to witness one of these dynamic events in great detail. Additional confirmation for the dust cloud theory was provided by observations from instruments capable of imaging the star with exceptionally high resolution. These images not only showed the darkened patch on the star, but also revealed faint structures reaching outward, consistent with a cloud of material moving away from the surface. Furthermore, infrared telescopes registered an increase in emissions from warm dust, confirming that new particles had indeed formed in the recent past. As each new piece of data came in, the evidence began to converge. The most likely scenario was that Betelgeuse had undergone a major outflow of gas, a process probably fueled by a combination of its natural pulsation and powerful convection. This ejected material then cooled and condensed to form a dust cloud that partially veiled the star's light from our view. As this cloud continued to expand and dissipate into space, the star's brightness gradually returned to normal. This formed the central pillar of the dust cloud theory, and it accounted for the vast majority of what astronomers had witnessed. And yet, even with this compelling explanation, certain details remained that did not align perfectly. For instance, the sheer quantity of material involved in the event seemed to be greater than what would be expected from a single convective episode. The plume itself appeared to be of an exceptional size, which suggested that several different mechanisms could have been working in concert, perhaps a rhythmic pulsation that happened to align with an especially powerful convective surge. There was also the puzzle of why the dust cloud materialized in its specific location. The stellar environment surrounding Betelgeuse is an intricate tapestry of matter, a landscape sculpted by past ejections and the star's own powerful radiation. Any new formations of dust can interact with these older clouds, creating complex patterns that are challenging to decipher from such a great distance. Beyond these specifics lay the wider scientific context. While Betelgeuse is certainly not unique among red supergiants in shedding mass or generating dust, it is one of the very few that is near enough to allow for this level of detailed study. This proximity means that every observed event offers exceptionally valuable data, but it also underscores the scarcity of similar stars for comparative analysis. It remains an open question: how much of Betelgeuse's behavior is standard for its stellar class, and how much might be anomalous? Making that distinction requires a great deal of time and observation. As the subsequent months unfolded, the star began to regain its former brilliance, while the dust cloud either dispersed or drifted out of our direct line of sight. The profound fading event that had so captivated observers around the world had concluded, Yet the wealth of data acquired during this period became the subject of intense ongoing analysis. Astronomers meticulously compared their observations against sophisticated computer simulations, tweaking various parameters to discover which blend of convection, pulsation, and mass ejection could replicate the star's observed behavior. While each new simulation brought the models closer to reality, none could perfectly account for every single observed detail. This outcome is not unusual in the scientific process, as nature seldom aligns perfectly with our simplified theoretical frameworks. Instead, such observations expose new layers of complexity, compelling scientists to develop more nuanced ideas and refined theories. The dust cloud hypothesis continues to be the most widely embraced explanation for the Great Dimming, but it is not the complete picture. The full narrative involves fluctuations in the star's surface temperature, variations in its pulsation cycles, and the complex architecture of its surrounding environment, all of which contributed to what we witnessed. The dimming event, in essence, was not the result of a single, isolated cause, but rather a convergence of interconnected processes within a system of breathtaking scale and intricacy. Long before Betelgeuse's dimming captured global attention, astronomers were well aware that this star lacked the steady nature of our own Sunday. For as long as precise measurements had been recorded, its luminosity had been observed to wax and wane. These fluctuations were not chaotic. They adhered to slow, methodical patterns that played out over months and years. The cause of these regular changes was not, in most instances, dust passing in front of the star. The variations originated from the star itself as it physically expanded and contracted, a gradual, rhythmic inhalation and exhalation of its vast outer layers. This is the phenomenon astronomers refer to when they speak of a pulsating star. The term pulsation might evoke the image of a rapid, steady beat, like a heart. For a star of Betelgeuse's magnitude, however, the process is profoundly slow. A single cycle of expansion and contraction can take well over a year to complete. During this cycle, the star's outer layers swell outward, cooling as their surface area increases. Subsequently, the immense force of gravity draws them back inward, causing them to heat up once more. These changes in temperature and surface area directly result in the observed shifts in brightness. These pulsations are an inherent feature of the physics governing a red supergiant. Deep in the stellar core, energy from nuclear fusion radiates outward through immense layers of superheated gas. Some of this energy can be momentarily held within regions where the gas becomes more opaque, meaning it is more effective at absorbing radiation. As energy accumulates in one of these opaque zones, it exerts an outward force, prompting the star's outer layers to expand. As these layers expand, the gas thins and becomes more transparent, which allows the trapped energy to escape more freely. With the outward pressure diminished, gravity once again takes over, pulling the layers inward and resetting the cycle. It is a delicate interplay of gravity, pressure, and radiation that repeats itself endlessly. For decades, astronomers have charted the pulsations of Betelgeuse, identifying at least 2 primary cycles. One of these rhythms has a period of roughly 400 days, while another, much longer cycle extends over several years. The superposition of these 2 rhythms results in a pattern of brightening and dimming that, while irregular in its fine details, is broadly predictable over time. Scientists monitoring Betelgeuse expected to see variations, but variations that fell within the established range of these known cycles. The dimming event of 2019 and 2020 did not conform to this established pattern. Nevertheless, the theory of pulsation remained crucial because it offered a potential explanation for how the necessary conditions for dust formation could have arisen. To understand this connection, it is helpful to visualize what occurs during one of these pulsation cycles. As the star's outer layers expand, the surface temperature decreases slightly, the gas becomes cooler and less dense, and the gravitational bond holding it to the star weakens. In this expanded state, it is easier for powerful convection currents to carry material upward, sometimes with enough force to push it beyond the star's gravitational influence entirely. If a stellar expansion of this kind were to occur at the same time as a particularly strong convective upwelling, a vast quantity of gas could be expelled into space. This ejected material then cools as it travels away from the star, eventually reaching temperatures low enough for molecules and then solid dust grains to condense. Pulsation, therefore, can set the stage for the formation of a dust cloud. This is the reason many astronomers are convinced that pulsation was a key factor in the Great Dimming, even if the dust cloud was the direct agent of the obscured light. There is compelling evidence to support this view. Brightness measurements of Betelgeuse in the years just before the dimming event indicated that the star was nearing a minimum in one of its pulsation cycles. Concurrently, its longer cycle was also trending toward a low point. The alignment of two separate cycles, both reaching a trough, could lead to a far more pronounced dimming than usual. The effect was analogous to two slow-moving ocean waves overlapping, their combined force creating a trough much deeper than either wave could produce alone. Yet even this more complex explanation was not entirely sufficient. The observed dimming was still more extreme than what pulsation alone would typically cause. This disparity suggested that while pulsation had prepared the conditions, another factor must have amplified the outcome. A further aspect of pulsation that captured the interest of astronomers is its effect on the star's atmosphere. As the outer layers expand and contract, they create powerful shock waves that propagate through the surrounding gas. These shocks can compress matter in some areas and accelerate it in others, adding to the complex patterns of mass loss seen around red supergiants. In the case of Betelgeuse, it is plausible that these processes worked in tandem with convection to generate the enormous plume of gas that would ultimately become the obscuring dust cloud. Another line of inquiry centered on the pulsation patterns of Betelgeuse and whether they were also undergoing a transformation. Following the dimming event, certain observations hinted that the star's rhythmic cycles had been subtly altered. The specific timing of its brightness fluctuations no longer perfectly aligned with established patterns, and it appeared some cycles were either more or less pronounced than they had been previously. This observation raised a fascinating possibility. As stars age, their internal structures are rearranged, and these internal shifts can in turn modify the periods of their pulsations. If the pulsations of Betelgeuse were indeed changing, it could be a sign that the star was transitioning into a new stage of its final evolutionary journey. While such changes would not necessarily signal an imminent supernova, they could offer valuable clues about the ongoing evolution deep within the star's interior. However, studying these pulsations in detail presents a considerable challenge. The outer layers of a red supergiant are chaotic and irregular, with the motion of gas being shaped by a host of factors, including powerful convection, the pressure of radiation, and the star's own rotation. To isolate the effects of pulsation from these other complex processes, a meticulous analysis of long-term observational data is required. Fortunately, because Betelgeuse has been monitored for such an extended period, astronomers possess a wealth of records to analyze. Photometric measurements, spectroscopic data, and various imaging studies combine to form a comprehensive picture of how the star's luminosity and surface features have varied over decades. By comparing these historical records against theoretical models, scientists can rigorously test their understanding of how stellar pulsations originate and how they interact with other phenomena in a star's atmosphere. One of the more compelling discoveries to emerge from these studies is that the pulsations in red supergiants are not always perfectly consistent. The cycles themselves can fluctuate in duration and intensity, and entirely new modes of oscillation may appear or vanish as the star evolves. In essence, the star's rhythmic breathing is not perfectly steady. There are times it seems to take a deeper breath, and other times when its exhalation lingers longer than anticipated. Over long timescales, the entire pattern gradually shifts. This inherent variability makes precise prediction exceptionally difficult. It also suggests that an event like the Great Dimming may not occur again in precisely the same manner, even if the fundamental mechanisms driving it are similar. Another element to consider is the sheer physical scale of these movements. When Betelgeuse expands during one of its pulsation cycles, its radius can increase by tens of millions of kilometers. The energy required to move such an immense volume of gas is staggering. The timescales involved are so vast that, to our eyes, the changes seem gradual, yet they represent dynamic processes of almost unimaginable power. If we could somehow witness the star from a much closer vantage point, its surface would not look serene or stable. It would present a landscape of slowly swelling and subsiding regions, with glowing clouds of material drifting upward, and vast currents of gas flowing in patterns that take months to resolve. From that intimate perspective, the dimming of Betelgeuse might not appear to be a sudden occurrence at all, but rather one phase within a continuous, grand process of motion and change. Yet, from our position on Earth, looking across hundreds of light years, those slow, massive processes become compressed into patterns of brightness that can seem quite abrupt. This difference in perspective is crucial. Astronomers must interpret these distant observations with great care, translating minor fluctuations in light into physical events happening on scales that defy easy comprehension. In the case of Betelgeuse, the theory of a pulsing star offers one vital piece of the overall explanation. It helps to account for the timing of the dimming and for the specific conditions that would allow dust to condense, but it does not resolve every mystery. The immense size of the dust cloud, the specific structure of the dimming event, and the concurrent changes in the star's surface features all point to the likelihood that several processes were working in concert. If you could be transported close enough to Betelgeuse to see it clearly, the first thing you would realize is its profound dissimilarity to our own Sunday. The Sun, even when viewed through advanced telescopes, appears relatively consistent, its surface marked primarily by sunspots and the occasional flare. Betelgeuse would be an entirely different spectacle. Its outer layers are so incredibly extended and so tenuously bound by gravity that the distinction between its surface and its atmosphere becomes indistinct. Instead of a sharply defined disk, you would perceive a vast, glowing expanse of gas, uneven in its brightness and in a state of constant, slow transformation. Astronomers often refer to this region as the photosphere, which is the layer from which the majority of a star's visible light is able to escape. On a red supergiant, however, this layer is neither thin nor stable. It is a deep, turbulent, and dynamic zone, sculpted by the movement of enormous currents of gas that rise and fall over immense distances. To grasp why this occurs, it is helpful to consider how energy moves from a star's interior to its exterior. Deep within the core of Betelgeuse, nuclear reactions are still taking place, generating energy that must find a path outward to be radiated into space. In smaller stars, such as the Sun, a great deal of this energy travels through a region where radiation carries heat outward in a relatively orderly fashion. But in the outer layers, where the gas grows cooler and more opaque, the primary mode of energy transport becomes convection. Convection is the same fundamental process we see in a pot of water heating on a stove. Water at the bottom warms, becomes less dense, and rises. Upon reaching the surface, it cools, grows denser, and sinks back down. This circulation creates a pattern of rising and falling currents that efficiently carries heat upward. On the Sun, convection takes place within countless small cells, each one roughly the size of a terrestrial country or continent. It is these cells that give the solar surface its characteristic grainy appearance when observed in high resolution. On Betelgeuse, the circumstances are vastly different. Because the star is so enormous and its surface gravity is so weak, convection operates on a truly colossal scale. Instead of thousands or millions of small cells, Betelgeuse may have only a few gigantic ones active at any given time. Each of these convection cells can span a significant portion of the star's radius, meaning a single rising plume of hot gas could be larger than the entire orbit of Earth. These currents move with incredible slowness, taking months or even years to complete a full cycle. Hot gas ascends from deeper layers, spreads out across the surface, radiates its heat away, and then sinks back down. This process is continuous but never perfectly uniform, and the star's surface brightness directly reflects these movements. Some areas appear brighter where hot material is rising, while others appear darker where cooler gas is sinking. From Earth, these patterns are exceedingly difficult to observe directly, but recent advances in a technique called interferometry have finally made it possible to resolve the surface of Betelgeuse in remarkable detail. Detailed images captured by powerful telescope arrays paint a picture of a star whose surface is anything but smooth and uniform. We see a mottled landscape of irregular bright patches interspersed with darker, cooler regions, confirming a constantly churning exterior. The scale of this boiling motion is almost beyond comprehension. This is not the gentle activity of a simmering pot, but a profoundly violent process fueled by immense reserves of energy. Each one of these enormous convective cells is responsible for carrying vast quantities of superheated gas and thermal energy up from the interior. At the boundaries where these neighboring cells interact, their powerful collisions can create incredibly strong flows that push stellar material outward with great force. Sometimes, these dynamic flows become so potent that they are able to lift huge volumes of gas entirely beyond the star's outer layers, launching it into space. It is this very mechanism of material ejection that provides a crucial link to understanding Betelgeuse's mysterious dimming. If a particularly large and energetic convective plume rises and manages to break through the outer atmosphere, it can successfully expel a massive cloud of gas into the void. As that liberated cloud of gas expands on its journey away from the star, it also cools significantly. This drop in temperature allows for conditions where individual atoms can begin to form molecules, which then coalesce. Eventually, this process leads to the appearance of tiny, solid grains of dust. Over time, such an eruptive event has the potential to produce a dust cloud so large and dense that it can obscure a part of the star when viewed from Earth. Observations strongly suggest that a sequence like this may have unfolded on Betelgeuse. Not long before the Great Dimming, a large portion of the surface was seen to brighten, possibly indicating a powerful upwelling of hot material from deep within. Later, that very same region appeared to darken, and a separate cloud of dust was detected nearby. It was as if the star had exhaled a vast plume of gas, which then drifted on an outward trajectory and partially blocked its own light. This intricate connection between convection and mass loss represents one of the most active areas of research in the study of red supergiants. Scientists are still diligently working to understand the exact interplay between these giant cells, pulsations, radiation pressure, and magnetic fields to fully explain how they drive the shedding of material. Another factor that further complicates the picture is the unique structure of Betelgeuse's atmosphere. Unlike our Sun, which has a relatively thin atmosphere compared to its radius, Betelgeuse possesses a hugely extended envelope of gas that stretches far out from its visible surface. This vast envelope is not at all static. It is a dynamic realm that constantly moves, expands, and interacts with the material being ejected from below. Within this expansive region, temperatures and densities can vary dramatically. Some areas are hot enough to emit strongly invisible light, while other, cooler zones radiate their energy mainly in the infrared. Dust is able to form in isolated pockets where the physical conditions are just right, creating an evolving patchwork of clouds and filaments over time. From our great distance, all of this staggering complexity is reduced to a single, simple number, the star's brightness. But what is remarkable is that this number reflects the combined effect of countless processes occurring across a region of space larger than our entire inner solar system. It is a powerful reminder of how much information can be hidden in something as seemingly simple as a point of light in the night sky. The boiling surface of Betelgeuse also helps explain why its brightness variations are not perfectly regular or predictable. In stars where pulsation is the dominant physical effect, the cycles of change can be relatively consistent, but in the case of Betelgeuse, convection introduces a profound element of irregularity. The size and strength of the individual cells change over time, and their complex interactions can produce fluctuations that do not follow a simple, repeatable pattern. The situation is somewhat similar to forecasting weather on Earth. We can predict general seasonal trends, but the specific details of storms and winds remain notoriously difficult to forecast far in advance. Astronomers sometimes employ sophisticated computer simulations to study convection in red supergiants, but these simulations are exceptionally challenging. Modeling the motion of gas on such truly enormous scales requires vast computational resources, and even the best models must simplify certain aspects of the underlying physics. Nevertheless, these simulations have revealed that the surfaces of red supergiants are indeed dominated by a small number of giant convection cells, and that these cells can produce large-scale brightness variations consistent with direct observations. They also show that the boundaries between these cells can be unstable, sometimes leading to sudden and dramatic changes in flow patterns. When such a change occurs, it can trigger the ejection of material into the surrounding space. That possibility fits very well with what astronomers observed happening on Betelgeuse. There is also compelling evidence that magnetic fields may play a role in shaping the surface and atmosphere of the star. While Betelgeuse's magnetic field is much weaker than that of the Sun, even a modest field can influence the motion of charged particles in the outer layers. This magnetic activity could help to channel gas into focus plumes or arcs, thereby contributing to the irregular structure of the material surrounding the star. This remains an area of active study, and many of the finer details are still uncertain. Another interesting aspect of Betelgeuse's surface is its temperature. Although the star is enormously luminous, its surface temperature is relatively low compared to many other stars, typically around 3,500 degrees C. This is precisely why it appears red to us, rather than white or blue. This cooler temperature also makes it significantly easier for molecules and dust to form in the outer layers. In hotter stars, such materials would be quickly destroyed by the intense and unforgiving radiation. In Betelgeuse, the conditions are far more favorable for the growth of complex molecules and tiny solid grains. Over long periods, these grains can accumulate in the surrounding envelope, contributing to the dusty environment that plays such an important role in the star's appearance and its long-term evolution. When astronomers look at Betelgeuse in infrared light, they can see this environment in remarkable detail. Great shells and sweeping arcs of material extend outward, providing clear evidence of past eruptions and ongoing mass loss. Some of these delicate structures are thousands of years old, slowly drifting away from the star and dispersing into the interstellar medium. This constant shedding of material means that Betelgeuse is gradually losing mass over tens of thousands of years. It will eventually shed a significant fraction of its outer layers, enriching the surrounding space with elements forged deep in its interior. But in the shorter term, this process creates a complex and changing environment that can influence how the star appears from Earth. During the Great Dimming, the intricate interplay between convection, pulsation, and dust formation likely reached an unusually dramatic combination. A large convective plume may have lifted material high into the atmosphere, where it then cooled and condensed into dust. That newly formed dust then drifted into our line of sight, effectively reducing the star's brightness. At the same time, changes in the surface brightness caused by the convection itself may have amplified the effect, making the dimming appear even more pronounced. Even now, astronomers continue to monitor Betelgeuse, watching vigilantly for new changes in its surface patterns and overall brightness. With every new observation, our comprehension of these gigantic stars becomes more refined. One of the most compelling aspects of this research is its ability to let us witness phenomena that were once confined to the realm of theory. 100 years ago, astronomers could only speculate about the inner mechanics of stars. Today, they are able to create images of the surfaces of faraway suns, follow the movement of gas and dust, and observe a star as large as a planetary system gradually alter its own shape. And yet, even with all these advancements, Betelgeuse continues to present us with surprises. Its surface is in a constant state of unrest. Its luminosity persistently fluctuates, and the precise forces that govern its activity are still not completely grasped. This very uncertainty is a significant part of what makes the star such a fascinating subject of study. The reason is that each time a new plume of material erupts, and each time a new cloud of dust materializes, we are offered another window into the life of a star, approaching the conclusion of its immense existence. As astronomers carefully study these transformations, comparing images captured months or even years apart, they are slowly assembling a more coherent view of how Betelgeuse is casting off its external layers into the cosmos. This process is not a smooth or consistent affair. Instead, it is erratic, at times gentle, and at other times unexpectedly powerful. It is a process that progressively strips away the star's outer envelope, transporting its substance into the void. Gaining a deep understanding of this mechanism is critical for resolving one of the most captivating questions about Betelgeuse. How much of the star's material has already been shed, and what implications this steady loss of mass might have for its ultimate fate? For the vast majority of human history, every star in the night sky shared a fundamental characteristic. Regardless of their brightness or faintness, or their particular color, they all registered as simple points of light. This perception did not significantly change even when the first telescopes were directed toward the heavens. Planets resolved into disks with moons and phases, but the stars themselves remained resolutely point-like, distant suns too remote to reveal any discernible surface. This fundamental limitation defined the field of astronomy for centuries. Scientists could gauge brightness, color, and movement, but the true visual character of a star's surface was concealed from view. The situation was somewhat like hearing a voice from behind a wall. One could know someone was there, and roughly how loudly they were speaking, but seeing their face was impossible. Betelgeuse was the star that changed everything. This is not because it is close in any conventional sense. A distance of 600 light-years is still a staggering expanse, far greater than anything humans can truly comprehend in physical terms. However, on the scale of our galaxy, it is a relatively close neighbor. More importantly, it is simply enormous. Its apparent size, as seen from Earth, while still incredibly small, is just large enough for modern instruments to begin resolving features across its visible disk. This capability was not achieved suddenly. It was the culmination of decades of technological advancement and the creation of innovative techniques that enabled astronomers to merge the light from several telescopes, in effect building a single virtual instrument much larger than any individual mirror could be. This method is referred to as interferometry. The principle of interferometry involves collecting light at multiple separate observatories and then combining those signals with exceptional precision. When executed correctly, this allows astronomers to attain a level of resolution equivalent to a telescope with a diameter equal to the separation between the individual instruments. In some instances, this virtual telescope can span hundreds of meters. Employing this technique, astronomers started to generate images of Betelgeuse that revealed something truly astonishing. The star was not a perfect, uniformly glowing sphere. Its surface was irregular, distinguished by brilliant hot regions and dimmer cool patches, all shaped by the massive convection currents that had long been predicted by theory but never before seen in such detail. For the very first time, scientists were not merely deducing what a distant star might look like. They were actually seeing it. The initial images were still somewhat indistinct, more like artistic impressions than sharp photographs. Yet even these early views showed that Betelgeuse was anything but smooth. As the techniques were refined over time, the images grew progressively clearer, exposing large-scale structures across the star's face. These observations served to confirm what theoretical models had been proposing for many years. The surface of a red supergiant is governed by a small number of colossal convection cells. Each of these cells carries energy from the star's interior up to its surface in slow, churning currents. But the images uncovered more than just convection. They displayed asymmetries in brightness that shifted over time, which suggested that the surface was in a state of perpetual motion, evolving over timescales of months and years. It was as if the star possessed its own form of weather, not weather involving wind and rain, naturally, but vast movements of gas and heat that reshaped its visible surface in ways that could finally be monitored and analyzed. Then came the great dimming event of 2019 and 2020. Suddenly, these imaging technologies took on an even greater significance. Astronomers understood that they had a unique opportunity to observe a profound change as it happened, not just by measuring brightness, but through direct images of the star's surface and its immediate environment. The Very Large Telescope at the European Southern Observatory, outfitted with advanced instruments built for high-resolution imaging, played an indispensable part. When observations taken before the dimming were compared with those taken during the event, the contrast was remarkable. A specific area of the star was noticeably darker than it had been previously. This was no minor alteration. The difference was so pronounced that even the processed images, which demand careful analysis, plainly indicated that a portion of Betelgeuse's face had faded relative to the rest. Concurrently, other observations picked up on material moving away from the star, a finding consistent with the creation of a dust cloud. By assembling these various pieces of evidence, astronomers started to construct a narrative of what had likely occurred. A massive plume of gas probably rose from the star's surface, cooled as it expanded into space, and condensed into dust that then partially blocked the star's light. At the same time, shifts in the convection patterns might have created a large, cool patch on the surface itself. It was the first time scientists could witness both the cause and the effect unfolding in tandem. This represented an entirely new milestone in the study of stellar evolution. In the past, astronomers had seen evidence of mass loss and dust formation around distant red supergiants, but they seldom possessed images with enough detail to connect those phenomena directly to particular features on a star's surface. With Betelgeuse, they could watch the entire process in action, which was like finally being able to see the face that belonged to the voice. A different perspective on Betelgeuse came from the Atacama Large Millimeter Submillimeter Array, a powerful network of radio telescopes known as ALMA, situated high in the Chilean desert. The particular strength of ALMA lies in its sensitivity to wavelengths much longer than visible light. This capability allows it to detect cooler gas and dust, which can be completely invisible to standard optical instruments. The data gathered by ALMA offered compelling new evidence of massive plumes of material extending outward from Betelgeuse. These findings confirmed that the star was shedding its mass through uneven, localized ejections, rather than through a smooth and uniform stellar wind. This detail helped to explain the highly irregular nature of the dimming event. The obscuring dust cloud was not a symmetrical shell that neatly enveloped the star. Instead, it was a dense and clumpy structure, its form dictated by the turbulent processes occurring on the stellar surface far below. Witnessing these details fundamentally altered how astronomers perceived red supergiants as a whole. The traditional idea of a steady, spherical loss of mass started to be replaced by a more nuanced understanding. This new model emphasized the dominant role played by giant plumes and vast arcs of gas. Betelgeuse was not simply exhaling its substance quietly in all directions. It was erupting in slow, powerful bursts, with each event actively reshaping its immediate cosmic environment. Another intriguing aspect revealed by these observations was the nature of the star's surface itself. It is not a solid, well-defined boundary, but rather a transitional region. The outermost layers are so incredibly diffuse that the line between the star and its surrounding atmosphere becomes indistinct. Gas rising from the interior can travel outward, gradually thinning and cooling as it expands, until it eventually merges with the surrounding stellar envelope. In this way, Betelgeuse lacks a sharp edge. It simply fades into the vacuum of space. This extended atmosphere makes direct imaging a significant challenge, yet it also contains a wealth of information. By analyzing how light is absorbed and re-emitted across different wavelengths, astronomers can create maps of the temperature and density of the gas at varying distances from the star. This process builds a three-dimensional picture of its outer layers. During the Great Dimming, these measurements showed that the region around Betelgeuse had grown even more complex, with new structures materializing within the gas and dust. Every new observation contributed another piece to the unfolding puzzle. However, despite this remarkable progress, imaging the surface of a star remains an indirect science. The images generated through interferometry are reconstructions, derived from intricate patterns of light that demand careful interpretation. They are not photographs in the conventional sense, but rather representations constructed from vast amounts of data. Even so, the level of detail that is now achievable would have been considered impossible just a century ago. It is an extraordinary thought that humans, from our vantage point on a small planet orbiting an average star, have developed the means to map the surface of a distant red supergiant hundreds of light years away. And what these maps show is a star in constant motion, a restless and evolving body. Its surface is sculpted by forces that operate on scales far beyond our everyday experience. For the scientists studying Betelgeuse, these images are far more than simple pictures. They are vital clues to the star's internal mechanics, providing evidence of how energy moves through its immense layers and how material is ultimately transported outward into space. Each bright region, every dark patch, and each plume of gas tells a part of this ongoing story. And that narrative continues to unfold. Even after the Great Dimming concluded and the star returned to its former brightness, astronomers kept observing Betelgeuse with the very same instruments, searching for any further changes. Some features on its surface appeared to shift. New patterns began to emerge. The surrounding clouds of material drifted and evolved. The star did not revert to the exact state it was in before the event. This, perhaps, is one of the most significant lessons from this period of intense observation. Betelgeuse is not a static object that experiences occasional disruptions. It is an inherently dynamic system in a perpetual state of change, sometimes gradually and at other times, far more dramatically. The dimming event was not an isolated anomaly, but was instead a visible part of a much larger, continuous process. What makes Betelgeuse so particularly captivating is not just that it changes, but that it is slowly disassembling itself. This is not happening violently, nor in a single, spectacular moment. It is a gradual and steady process that has likely been underway for tens of thousands of years. Every second, enormous quantities of gas drift away from the star, spreading out into the surrounding darkness and becoming part of the vast, tenuous medium that exists between the stars. In a very tangible sense, Betelgeuse is losing itself to space. This phenomenon is not unusual for a red supergiant, but the sheer scale at which it occurs is difficult to fully comprehend. Our own sun also loses material. The solar wind carries a constant stream of particles outward, but the total amount is relatively minor compared to the sun's overall mass. Betelgeuse, in stark contrast, is shedding material at a rate millions of times greater. Over the remainder of its existence, it will lose a substantial fraction of its outer layers before its life finally comes to an end. To understand the reason for this, it is helpful to consider gravity and how its influence changes over the course of a star's life. It is gravity that holds a star together. For smaller stars like our Sun, the gravitational pull at the surface is strong enough to keep its gases tightly bound. Even powerful solar flares and eruptions typically see their material fall back to the surface or disperse very slowly, but for a red supergiant, the situation is profoundly different. As a massive star ages and swells, its outer layers are spread across a much larger volume. The mass remains, but it is distributed over an immense radius. Consequently, the force of gravity at the surface becomes incredibly weak, sometimes thousands of times weaker than at the surface of the Sunday. This means that far less energy is required to lift material away from the star and into space. At the same time, the star's luminosity is tremendous. Radiation pressure, which is the outward push exerted by light itself, becomes a significant force influencing the motion of gas and dust. As photons stream away from the surface of Betelgeuse, they carry momentum. When these photons collide with particles in the star's outer layers, they transfer a tiny amount of that momentum. Individually, these pushes are minuscule, but with countless photons radiating outward every second, their cumulative effect can help drive material away from the star. Convection introduces another layer of complexity to this process. The gigantic convective cells rising and falling across the surface of Betelgeuse can carry gas to very high altitudes within the atmosphere, where gravity is even weaker. Once there, radiation pressure and the star's natural pulsations can push this material even farther out, allowing it to escape the star's gravitational hold entirely. This is not a smooth, gentle outflow. It is an irregular process, sometimes calm and sometimes more energetic, shaped by the shifting patterns of convection and the star's own pulsation cycles. When astronomers examine Betelgeuse in infrared light, the effects of its continuous mass loss become visible. Vast arcs and shells composed of gas and dust encircle the star, with some structures having formed quite recently and others being thousands of years old. These formations move outward at a rate of several kilometers per second, slowly expanding as they merge with the interstellar medium. Each arc signifies a distinct episode of mass loss, a period when the star ejected a greater than usual amount of its substance. Over immense timescales, these events accumulate, constructing a layered chronicle of the star's outer regions being carried away into space. If one could witness this phenomenon up close, it would lack the sudden drama of an explosion. The movement would be gradual, almost tranquil, with clouds of glowing gas expanding deliberately, drifting outward like mist settling in calm air. The scale of it all, however, would be astonishing. A single cloud might hold sufficient material to create planets, or potentially entire planetary systems, given the necessary time and conditions. This material is far from empty. It is rich with elements that were forged deep within the star's core. Among them are carbon, oxygen, and nitrogen elements that are fundamental to the formation of molecules, rocks, oceans, and life itself. Long before our own Earth came into being, other stars underwent similar processes, shedding matter that would eventually become integrated into the nebula from which our solar system was born. In this way, the slow unraveling of Betelgeuse is an extension of the same cosmic cycle that ultimately led to our existence. From a scientific standpoint, however, the precise details of how this mass loss occurs are not yet fully understood. A significant challenge is that multiple processes are at play simultaneously. Pulsations cause the star to rhythmically expand and contract, which in turn alters the density and temperature of its outer layers. Convection generates localized upwellings of hot gas that can breach the surface. Once dust grains form, radiation pressure from the star pushes them outward. Furthermore, magnetic fields, while not as strong as in smaller stars, might still guide the motion of charged particles. Each of these forces interacts with the others in ways that are incredibly complex and difficult to simulate accurately. Observations of Betelgeuse have revealed that the loss of mass is not distributed evenly across its surface. Instead, material frequently emerges in large plumes or arcs that are concentrated in specific regions. This pattern strongly suggests that convection plays a dominant role, with gigantic cells lifting gas in localized bursts rather than the entire surface shedding material in a uniform manner. During the Great Dimming event, astronomers likely observed one of these bursts in real time. A massive plume of gas rose from the surface, cooled enough to form dust, and then drifted away, partially blocking the star's light from our view. But that particular plume represented only a single moment in a much longer, ongoing process. Over many thousands of years, Betelgeuse has constructed an extended envelope of material around itself. Some of this matter remains relatively close to the star, where it is still warm enough to glow faintly. Other clouds have journeyed far enough to cool and disperse, gradually blending into the tenuous gas that permeates interstellar space. When astronomers map this surrounding environment with radio and infrared telescopes, they uncover a complex tapestry of shells and filaments, which stands as evidence of repeated episodes of mass loss over eons. It is akin to examining the rings of a tree, except that instead of being neatly concentric, these layers are distorted, stretched, and scattered by turbulence and motion. Another element that contributes to the shedding of mass is the star's temperature. Although Betelgeuse is exceptionally luminous, its surface temperature is comparatively low when measured against many other stars. This cooler environment allows molecules to form in the outer atmosphere, and these molecules can then more easily coalesce into dust grains than they could in hotter stars. As soon as dust forms, the outward push from radiation pressure becomes substantially more effective, because dust grains interact very strongly with light. In this sense, the dust behaves almost like a sail, catching the star's radiation and dragging the surrounding gas along with it. This feedback mechanism, where convection lifts gas, dust forms, and radiation pressure pushes it all outward, helps to sustain the mass loss over very long periods. Even so, certain aspects of Betelgeuse's behavior continue to be a source of puzzles. The rate at which it loses mass seems to fluctuate over time, occasionally increasing dramatically for brief intervals. The mechanisms that trigger these heightened episodes are not always clear. They might originate from changes occurring deep inside the star, or they could arise from the chaotic interplay of convection and pulsation near the surface. Gaining a better understanding of these variations is critical, because mass loss is a key factor in determining how a massive star concludes its life. As Betelgeuse sheds its outer layers, its internal structure is altered. The core continues its evolution, fusing progressively heavier elements, while the surrounding envelope grows thinner and becomes less gravitationally bound. Ultimately, when the core collapses, the nature of the material around it will influence how the resulting supernova unfolds, shaping both the shockwave and the light that travels to distant observers. In other words, the slow, steady loss of mass happening now will help define the character of the final, cataclysmic explosion whenever it happens. From a human viewpoint, it can be challenging to conceive of a star as something that can fade, come apart, and vanish. Stars often feel permanent, almost eternal, but they are in fact temporary structures held in a delicate balance of forces that must eventually shift. Betelgeuse is simply far enough along in its life that we are able to witness that shift as it occurs. Even at this moment, as its light travels to Earth night after night, streams of gas are continuously drifting away from its surface. These streams are invisible to the naked eye, but are readily detectable with sensitive instruments. Each plume carries away a small fraction of the star, adding to the vast, diffuse clouds that populate the galaxy. And yet, despite losing so much material, Betelgeuse remains enormous and brilliant, holding its place as one of the most prominent stars in our sky, still shining with the energy of nuclear reactions deep within its core. This contrast between the immense scale of the star and the gradual nature of its decline is part of what makes it such a compelling object of study. Astronomers persist in their careful watch, measuring the velocity of the outflowing gas, analyzing the composition of the dust, and tracking the changes in brightness that signal new eruptions. Each new observation contributes to a growing, more detailed picture of how massive stars shed their outer layers, preparing slowly and almost imperceptibly for the final chapters of their evolution. Even after months of dedicated observation, countless measurements, and meticulous comparisons with theoretical models, there remained facets of Betelgeuse's behavior that could not be neatly explained by any single theory. The dust cloud theory offered a substantial explanation for the dimming, while pulsations helped to account for its timing, and convection clarified the mechanism for lifting material away from the star's surface. Even so, when astronomers scrutinized the data, there were still persistent details that defied a simple explanation. These were subtle discrepancies between prediction and observation, small mismatches that hinted at complex processes not yet fully grasped by science. This is a common circumstance in scientific exploration, where the broad outlines of a phenomenon can be well established, even as the finer points remain elusive. In the case of Betelgeuse, these finer details are profoundly important, as they reveal just how intricate the final chapters of stellar evolution truly are. One of the first unresolved questions concerned the sheer magnitude of the mass ejection that came before the Great Dimming event. Observations strongly suggested that a truly significant quantity of material had been cast off from the star's surface, enough to create a dust cloud so dense it could dramatically reduce the star's apparent brightness. However, the existing models of convection and pulsation did not consistently generate eruptions of that enormous size under what would be considered normal stellar conditions. This discrepancy raised the intriguing possibility that something highly unusual had transpired deep inside the star, perhaps a rare combination of physical processes working in concert in a way that is difficult for simulations to replicate. While convection by itself can elevate material, the largest plumes anticipated by current models are still considerably smaller than the scale inferred from the observations of Betelgeuse. Pulsations are known to amplify these effects, but the specific timing and intensity of the star's fading suggested that the interplay between these two processes might be far more complex than previously imagined. Another significant uncertainty revolved around the temperature of the star's surface during the dimming period. Measurements did indicate that the surface had cooled slightly, but this cooling was not nearly sufficient to explain the full extent of the decrease in brightness. This confirmed that the dimming was not purely a temperature change, yet the precise contribution of surface cooling versus the obscuring effect of the dust cloud remained difficult to pin down with certainty. Part of this challenge is rooted in the fact that Betelgeuse does not possess a uniform surface. Instead, different regions across its vast expanse can have different temperatures, and these thermal zones evolve over time. When astronomers measure the star's overall light spectrum, they are effectively averaging the light from all of those disparate regions, which makes it incredibly difficult to isolate changes happening in specific locations. High-resolution imaging certainly helps to mitigate this issue, but even the most advanced images are limited in their level of detail compared to what would be required to map the entire surface completely. There is also the fundamental question of how dust can form so efficiently within the environment immediately surrounding Betelgeuse. The formation of dust grains requires a specific set of conditions, including temperatures low enough for molecules to bond together, densities high enough for frequent collisions to occur, and enough time for these microscopic particles to grow. The outer atmosphere of a red supergiant is not always a stable or hospitable place for such formation processes. Intense radiation and turbulent gas motion can easily disrupt the delicate work of grain formation. And yet, in the instance of the Great Dimming, dust appeared to have formed with remarkable speed and in very large quantities. This observation suggests that there may be localized pockets where conditions become unusually favorable for dust creation, perhaps deep within the dense plumes of gas lifted by convection. The precise details of how these favorable regions form and evolve, however, are still being actively investigated. Another missing piece of the puzzle involves the intricate structure of the material that envelops the star. Observations have revealed a complex tapestry of arcs, clumps, and filaments of gas and dust extending far outward from Betelgeuse. These structures do not form the simple, uniform spherical shells that early models once assumed. Instead, they appear to be the result of episodic and asymmetric eruptions. Understanding what triggers these eruptions and why they seem to occur in some regions of the star but not others remains a major open question in astrophysics. Magnetic fields might play a crucial role in this process, but the magnetic field of Betelgeuse is exceptionally difficult to measure directly, and consequently, its strength and overall structure are not well known. Even a relatively weak magnetic field could profoundly influence the motion of charged particles in the star's atmosphere, thereby shaping the flow of gas and contributing to the formation of massive plumes. But without precise measurements, this idea remains in the realm of well-informed speculation. Rotation is another factor whose influence is not fully understood. Betelgeuse rotates very slowly, but even a slow spin can affect the distribution of material in its outer layers, potentially altering convection patterns and influencing where mass loss is most likely to occur. Determining the exact rotation rate of a star with such an extended and irregular atmosphere is a formidable challenge, and different scientific studies have produced slightly different results. Then there is the deeper question of what is unfolding in the star's hidden interior. The core of Betelgeuse is completely obscured from direct observation, compelling astronomers to rely on theoretical models to infer its structure. These models suggest that the star is currently fusing heavier elements in a series of shells that surround a contracting central core. The details of this process, however, depend on a number of assumptions about internal mixing, convection, and nuclear reaction rates that are still being refined. Small changes in these parameters can significantly affect predictions about the star's observable behavior, including its pulsation periods and its rates of mass loss. Some researchers have put forward the idea that Betelgeuse may be in a transitional phase, shifting from one stage of core fusion to the next. Such transitions can alter the star's energy output and the structure of its outer layers, potentially triggering unusual activity on the surface. Confirming this hypothesis, however, will require much more data and the development of more sophisticated models. There are also lingering uncertainties in the exact distance to Betelgeuse, a measurement which directly affects our estimates of its true size and luminosity. Although recent measurements have greatly improved the precision of these distance estimates, small remaining differences can still lead to significant changes in its calculated properties, and those properties in turn influence the models of the star's past and future evolution. Another intriguing puzzle concerns the long-term variability of Betelgeuse. Historical observations, including records from centuries ago, suggest that the star's brightness may have varied more widely than was previously thought. Some studies of ancient and medieval records hint that Betelgeuse may have been significantly fainter at certain times in the distant past. If this were proven true, it would imply that events like the recent dimming are not unique, but are instead part of a much longer pattern of variability that spans many centuries. Interpreting these historical records, however, is exceptionally difficult. Descriptions of brightness are often qualitative, and any comparisons made to other stars depend on atmospheric conditions that are not always known. So, while these fascinating old accounts are highly suggestive, they cannot provide definitive answers about the star's long history. These observations, however, suggest the possibility that the behavior of Betelgeuse is far more intricate and variable than our modern records alone can capture. One of the most significant hurdles in understanding this star is the immense spectrum of timescales that govern its existence. The slow, churning motion of convection deep within its envelope unfolds over months or years. Its fundamental pulsations, the rhythmic breathing of the star, have cycles that last for years. Episodes of significant mass loss can require decades to fully manifest, and changes originating in the core might take thousands of years before their effects ripple outward to the visible surface. From our human vantage point, we are witnessing only the briefest of moments in a process that spans millennia. This vast temporal scale makes it exceptionally difficult to place contemporary events into their proper context. Was the Great Dimming a singular event, or was it merely one phase in a much longer, unseen trend. Are the pulsation patterns we currently observe typical for the star, or do they signify a temporary state of being? These are questions that may require decades of continuous observation to begin to answer. There is also the wider challenge of connecting what we see at Betelgeuse with observations of other red supergiants. Each of these stellar giants has its own unique character, and while they follow general patterns of evolution, their individual differences can be quite substantial. The specific phenomena occurring on Betelgeuse may not be a perfect mirror for what happens on other stars of a similar mass and age. This reality means that astronomers must exercise great caution when attempting to generalize from a single case, even one that has been studied as extensively as this one. And yet, despite the layers of uncertainty, our understanding continues to advance. A new generation of instruments, located both on the ground and in orbit, is delivering data with unprecedented detail. Observations across multiple wavelengths of light, from radio waves to the ultraviolet, are uncovering different facets of the star and its surrounding environment. At the same time, computer models designed to simulate its behavior are growing ever more sophisticated, capable of incorporating more nuanced physics and achieving higher levels of resolution. Every new piece of information helps to fill in the remaining gaps in our knowledge. The picture, however, is still far from complete, and perhaps this is the source of its deep fascination. Betelgeuse serves as a powerful reminder that even with all our accumulated knowledge, the cosmos is still filled with profound mysteries. It contains objects that behave in ways we cannot yet fully explain, and processes that challenge our theoretical models, compelling us to look ever more closely. The star itself carries on, changing with a slow and quiet persistence, shedding its material into space, pulsating, and continually reshaping its turbulent surface. Each night, it rises and sets, just as it has for centuries. But now, we watch it with a renewed focus, conscious that something truly unusual has transpired and that more surprises may yet be in store. It is nearly impossible to witness a star like Betelgeuse transform without considering the question that sits quietly in the background of every conversation about red supergiants. It is not a dramatic inquiry, nor one that scientists pose with any sense of urgency, but it is a thought that inevitably surfaces. Is this the start of the final act? This idea arises naturally from the knowledge that Betelgeuse is approaching the last stages of its stellar life. This end is not expected tomorrow, nor next year, but within the grand sweep of cosmic time, the star is undeniably closer to its conclusion than its inception. The hydrogen fuel in its core was depleted long ago. The star has already swelled into the immense form of a red supergiant. It is now fusing heavier elements in a series of concentric layers, a process that is slowly building toward an inevitable tipping point where the outward push of fusion can no longer counteract the immense weight of the star pressing inward. When that moment finally arrives, its end will be anything but quiet. A massive star does not fade away gently into the night. Instead, it collapses under its own gravity and then rebounds in a supernova, an explosion that unleashes an extraordinary quantity of energy in a very brief span of time. For a period of weeks or months, the exploding star can outshine billions of its neighbors combined. The resulting shockwave expands outward at incredible speeds, scattering newly forged heavy elements across interstellar space, while the remnant of the core collapses into either a neutron star or a black hole. This is the ultimate destiny that awaits Betelgeuse. But knowing that a star will one day explode is a very different matter from knowing when. One of the most critical concepts in stellar evolution is that the final phases, while brief compared to a star's total lifespan, are still incredibly long on a human scale. A red supergiant can exist in the same phase as Betelgeuse is in now for tens of thousands of years. The changes that astronomers observe as rapid, such as variations over mere years or decades, are still just tiny fragments of a much longer narrative. For this reason, when Betelgeuse dimmed so dramatically, astronomers did not immediately conclude that a supernova was imminent. Instead, they posed a more measured and careful question. Were there any signs indicating that the star's core was nearing the point of collapse? The physical processes that trigger a supernova actually begin deep within the star, far beneath the photosphere we can see. The outer layers might respond to these deep internal changes, but those responses are often indirect and can be extremely subtle. To appreciate what scientists search for, it is helpful to review what occurs inside a massive star as it approaches the end. Nuclear fusion proceeds through a sequence of stages. Once hydrogen is exhausted, helium fusion begins, and after helium, the star starts to fuse heavier elements like carbon and oxygen. Each of these fusion stages takes place in a shell surrounding the core, and each successive stage lasts for a significantly shorter duration than the one before it. Hydrogen burning can persist for millions of years. Helium burning might last for hundreds of thousands of years. The very last stages, involving elements like silicon, can be completed in a matter of days. Betelgeuse, however, is not believed to have reached those final, frantic stages just yet. The majority of models indicate that it is currently in the process of burning helium, or perhaps just beginning to fuse heavier elements in its deeper layers. This implies that the final collapse is still far enough in the future that we should not expect to see any immediate warning signs. And yet, stars do not always adhere to our simplest predictions. There have been recorded instances of massive stars exhibiting unusual variability, or episodes of intense mass loss in the years or decades leading up to their explosion. In some of these cases, astronomers observed sudden outbursts, violent eruptions of material, or significant changes in brightness that hinted at a growing instability within the star's outer layers. This historical context is precisely why the dimming of Betelgeuse commanded so much attention. The interest was not because it proved a supernova was coming soon, but because it introduced the possibility, however remote, that something of consequence might be changing deep inside the star. Scientists began to meticulously examine all the available data, searching for patterns that could point to deeper transformations. They studied the star's pulsation periods, its surface temperature, the velocity of gas flowing away from it, and the composition of the surrounding dust clouds. What they ultimately found was intriguing, but it was not alarming. The evidence indicated that the dimming was caused primarily by surface-level activity and the formation of dust, not by a fundamental shift in the star's internal energy production. The temperature of the photosphere had not experienced a drastic drop. The star's spectral lines showed no evidence of the rapid structural changes in the deeper layers that might precede a collapse. In other words, while the star was certainly behaving in an unusual manner, it was not doing so in a way that suggested its immediate demise. Understanding this difference is fundamental. The outermost layers of a red supergiant possess an inherent lack of stability. A turbulent mix of convection, pulsation, and the outward push of radiation pressure results in a highly complex environment. Within this setting, massive eruptions and significant fluctuations can take place, having no direct relationship with the concluding phases of the star's core evolution. The situation is somewhat analogous to the weather systems on a planet. Storms can manifest with great power and unpredictability, yet they do not signal that the planet itself is on the verge of a fundamental transformation. Nevertheless, the potential for a future supernova is very real, making it worthwhile to contemplate what such an event would signify, both for science and for our view of the sky. Should Betelgeuse detonate, the resulting display would be nothing short of spectacular from our terrestrial viewpoint. At its most luminous, its brightness could match or even surpass that of the full moon. It would become a feature of the daytime sky, visible as a dazzling point of illumination against the blue. By night, it would be powerful enough to cast subtle shadows and would utterly command the constellation of Orion. The event would not, however, pose any danger to us. Situated at a distance of approximately 600 light-years, the energy arriving at Earth would be far too diffuse to inflict any harm. This explosion would be a celestial marvel to witness, not a menace to fear. For astronomers, it would present an unparalleled opportunity to examine a nearby supernova with incredible precision. They could observe the entire evolution of the blast from its very inception and monitor the expansion of its debris field over subsequent years and decades. Yet, for all the excitement this possibility generates, the most probable scenario is that Betelgeuse will simply persist as it has for millennia. It will continue to pulsate, to shed its mass, and to fluctuate in brightness, without actually exploding for a very long time to come. Herein lies one of the inherent challenges in conveying the realities of astronomy. We, as human beings, are naturally captivated by dramatic occurrences and moments of abrupt transformation. The cosmos, however, frequently operates on much slower, more consistent timescales. where the most significant processes develop in a gradual manner. The great dimming of Betelgeuse was certainly dramatic enough to seize global attention, but within the grand narrative of the star's existence, it may have been just one of many comparable episodes. It was likely part of the continuous loss of material that is a defining characteristic of the red supergiant phase. Another element to take into account is the extreme difficulty of predicting supernovae. Even with our most sophisticated models, astronomers cannot simply observe a star and declare with certainty how many years it has left before it goes critical. The internal mechanics are exceedingly complex, and many crucial details are governed by factors that we cannot measure from afar. What scientists are able to do is provide estimated ranges, pinpoint specific stages of stellar evolution, and maintain a watch for indicators of swift change. To date, Betelgeuse has exhibited none of these telltale signs. There have been no abrupt spikes in neutrino emission, nor any dramatic alterations in its spectral features that would suggest rapid developments within its core. We have also seen no sustained surge in energy output that might signal an imminent collapse. What we observe instead is a star behaving exactly as an aging red supergiant should. It is restless, it is variable, and it is shedding its outer layers, but its fundamental structure remains stable. And yet, this very uncertainty contributes to the star's deep fascination. Because Betelgeuse is near enough and massive enough, we are able to monitor it in exquisite detail, night after night and year after year. We are not merely studying the end of a star's life in the abstract. We are privileged to be watching one of the closest examples of this process as it happens in real time. This is an exceptionally rare privilege in the field of astronomy. It also serves as a potent reminder that the celestial sphere is not a static backdrop. The stars we gaze upon today will not exist in their current form forever. Some are destined to fade away, while others will explode, and still others will collapse into objects too small and dense to be seen with the naked eye. One day, Betelgeuse will become part of that cosmic story, but that day is not tonight. Tonight, it continues to glow, a deep reddish point of light on the shoulder of Orion. It is still losing mass, still shifting and pulsing, and still providing fresh data to the telescopes that scrutinize it with such care. As astronomers carry on with their observations, they are not only asking if the end is near, they are also posing a different, and perhaps more captivating, question. If Betelgeuse were to finally explode one day, what would that cataclysm actually look like from our vantage point on Earth? Just how luminous would it become? For how long would it shine? And how would the night sky itself be transformed during those weeks or months when one of our most recognizable stars suddenly became something else entirely? Imagine stepping out into the cold, clear air of an evening and turning your gaze toward Orion, anticipating the familiar celestial pattern. You expect to see the three bright stars of the belt, and above them, the characteristic reddish hue of Betelgeuse, as steady and serene as it has always appeared. On this particular night, however, something is profoundly different. The red star is no longer red in the way you remember. It has become brighter, sharper, with an almost white-hot center, and it is undeniably more luminous than any other object in the entire constellation. At first, you might wonder if your eyes are deceiving you. Stars can certainly seem brighter on nights of exceptional clarity, and Orion often appears especially vivid in the crisp winter atmosphere. But this change would be far from subtle. Within a matter of days, or possibly even hours, it would be unmistakably clear that Betelgeuse had undergone a monumental change. A supernova does not commence with an explosion that is immediately visible to faraway observers. Its initial stages are concealed deep within the star's interior, as the core gives way and a powerful shockwave starts to race outward through the overlying layers of gas. That journey takes time, often measured in hours or sometimes longer, before the shock finally breaks through to the surface and the star erupts in brightness. From our perspective on Earth, we would witness this as a rapid escalation in luminosity over a span of several days. Night after night, the star would appear more brilliant than it had the night before. The first to notice would likely be amateur astronomers, who would compare their measurements and quickly realize the ascent in brightness was far beyond any normal fluctuation. Professional observatories would then pivot their instruments toward Orion, confirming what the incoming data already implied. Betelgeuse would have begun the final, radiant phase of its existence. In about a week or two, the star's brilliance might come to rival that of the full moon. It would not diffuse its light across the heavens in the same manner as the moon, because it would remain a single point of light, but its intensity would be sufficient to cast faint shadows on the ground in locations free from light pollution. The constellation of Orion would no longer appear as it once did. The familiar balance of its stars would be completely upended, dominated by this one resplendent newcomer. People everywhere would take notice. Even individuals who seldom look up at the night sky would hear the news and step outside to see this new star shining brightly where a familiar one had been. At its zenith, the supernova could even be visible during the day, presenting itself as a bright dot against the blue expanse of the sky, a phenomenon that has not been witnessed in our region of the galaxy for many centuries. Such remarkable events have, in fact, been described in historical records. A historical parallel offers a glimpse of what to expect. Back in the year 1054, people in China and across the globe witnessed a star so luminous it was visible in daylight for several weeks. The aftermath of that ancient explosion is something we can still see today through telescopes. The beautiful, expanding remnant known as the Crab Nebula. Were Betelgeuse to undergo a similar cataclysm, it would offer a comparable spectacle in our own skies, though the details of the display would hinge on the specific mechanics of the explosion itself. Its moment of peak brilliance would be relatively brief, as after attaining its highest luminosity, the supernova would commence a gradual, extended fade. Over the following weeks and months, the star's light would slowly diminish, yet it would stay prominent enough for unaided eye viewing for a considerable period. Throughout this time, astronomers would be engaged in continuous observation, meticulously measuring the light spectrum, tracking the outward expansion of the ejected stellar material, and studying the shock wave's interaction with the surrounding gas. From our vantage point on Earth, the transformations would appear subtle yet distinct. A slight change in the light's color could occur as the expanding shell of gas lost heat, and its brightness would decrease incrementally from one night to the next. The change would not be so abrupt as to be obvious over a single evening's watch. For dedicated observers of the night sky, the experience would be akin to watching a far-off lantern grow steadily fainter, a poignant reminder that they were witnessing the cooling embers of one of the cosmos's most energetic phenomena. An intriguing dimension to such an event involves the time lag between the explosion and its other, less visible messengers. For instance, neutrinos, nearly massless particles generated in vast quantities during the core's collapse, would arrive at Earth ahead of the light, passing through our entire planet with almost no interaction. Deep underground, sensitive detectors might register a sudden surge of these particles hours before the supernova becomes visible to our eyes. It is also possible that gravitational wave observatories could pick up a faint signal, its characteristics dependent on the specifics of the collapse. Such measurements would offer invaluable data about the internal mechanics of the explosion, providing insights that light alone cannot reveal. For the vast majority of people, however, the experience would be a purely visual one, a brilliant new point of light adorning the sky, visible even during twilight, before it slowly receded over months. As time marched on, telescopes would unveil greater detail. The single point of light would gradually resolve into a tiny disk, which would then expand into a faint, glowing cloud as the ejected matter traveled outward. Many years later, long after the supernova's light had dimmed beyond naked eye visibility, a nebula would persist, an expanding shell of gas illuminated by the residual energy of the blast. At the heart of this new nebula, a neutron star might be found, an object of incredible density, where a mere teaspoon of its substance would weigh billions of tons as it spins rapidly and emits powerful beams of radiation. Alternatively, if the star's core were sufficiently massive, it could collapse completely into a black hole, an object detectable only through its gravitational pull on nearby gas. This entire cosmic evolution would unfold across decades and centuries, long after the initial flash had vanished from sight. It is equally important to reflect on what a Betelgeuse supernova would not cause. Despite the immense energy unleashed, it would present no threat to our planet. Situated at a distance of roughly 600 light-years, the radiation reaching Earth would be far too diluted to damage our atmosphere or harm life on the surface. The event would be a magnificent spectacle, not a terrestrial catastrophe. There could be minor effects that only sensitive instruments could detect, such as a slight increase in cosmic rays in the upper atmosphere, or perhaps subtle disturbances in the ionosphere. However, nothing would be noticeable in our daily lives. The sky above would be temporarily altered, but the world below would proceed unchanged. There is a quiet reassurance in this realization. The universe is capable of producing events of truly extraordinary power, yet the sheer vastness of space acts as a protective buffer, ensuring such phenomena remain distant and beautiful rather than dangerous and destructive. Predicting the precise brightness of a Betelgeuse supernova is, of course, a complex challenge. A supernova's luminosity is influenced by numerous factors, including the star's total mass, the chemical makeup of its outer layers, and the structure of the material it has already shed into its surroundings. Betelgeuse has already ejected a substantial amount of its mass, which has formed a complex environment of gas and dust around it. When the shockwave from the explosion plows into this pre-existing material, it could trigger secondary bursts of light, creating fluctuations in the supernova's brightness over time. Indeed, astronomers have witnessed similar effects in other supernovae, where interactions with circumstellar gas can cause secondary peaks in the light curve. These are brief intervals where the object's brightness intensifies again, before resuming its overall fade. Consequently, the celestial show might not be a simple, steady dimming. It could feature moments of renewed luminosity, subtle shifts in color, and other dynamic features that would keep observers captivated night after night. The matter of perspective is also worth considering. From our terrestrial viewpoint, the supernova would look like a single, brilliant point, but in reality, it would be an expanding sphere of incandescent gas, growing to be thousands of times larger than the original star within just a few weeks. The amount of energy liberated by the explosion would be astonishing, equivalent to the total energy our own sun is expected to produce over its entire multi-billion-year lifespan, all released in a few moments. Comprehending such a scale is difficult. It helps to remember that the universe operates on levels of energy and distance far beyond human experience. For anyone who appreciates the night sky, such an event would be truly unforgettable. Future generations of astronomers and casual stargazers alike would recall where they were when Betelgeuse finally exploded, a memory akin to great eclipses or the passage of rare comets. Yet, for all the fascination this prospect holds, it is crucial to return to the present. Betelgeuse has not yet gone supernova. It continues its existence as a red supergiant variable and restless, but fundamentally stable. Its core is still fusing elements, generating the outward pressure needed to support its immense weight. The famous Great Dimming was not the prelude to its imminent demise. Instead, it was a dramatic but temporary surface event, a powerful illustration of the dynamic nature of these massive stars, even when they are not in their final moments. Even so, contemplating what its supernova would look like provides a valuable context for the star's current behavior. This exercise reminds us that Betelgeuse is far more than just another point of light in the constellation of Orion. It is a colossal star approaching the end of its life cycle, slowly shedding its outer layers and evolving toward a fate that, while inevitable, is not immediately upon us. Once the extraordinary dimming event concluded, Betelgeuse gradually began to reclaim its former luminosity. The night sky started to appear familiar again, and the constellation of Orion regained its customary form. The reddish point of light on the hunter's shoulder shone with a renewed steadiness, enough so that an uninformed person looking up might not have realized anything strange had occurred. Scientists, however, held a different perspective. Even with the star's apparent return to calm, the collected information revealed that its behavior was not quite the same as it had been previously. Its cycles of brightness, which had once been fairly predictable, now seemed to be altered. Certain fluctuations in its light were more intense than anticipated. Others, by contrast, were more subdued or slightly misaligned with the timing of earlier records. What this means is that while Betelgeuse had settled down, it had not resumed its prior cadence. To appreciate the significance of this, it is useful to consider the methods astronomers employ to study variable stars. They no longer rely on judging brightness by eye, a practice that defined the field centuries ago. Today's instruments can measure luminosity with incredible precision, monitoring even minor fluctuations over time and translating them into graphs that show patterns the naked eye could never detect. Before its great dimming, the light curve for Betelgeuse, the official record of its brightness, displayed familiar, repeating cycles. It certainly had its inconsistencies, but its general conduct was well understood. Following the event, however, those established patterns appeared transformed. One of the notable changes concerned the amplitude of these variations, which is the measure of how much the star's brightness would increase and decrease. Some of its cycles grew more extreme, while others seemed to be suppressed. This observation hinted that the pulsations within the star's outer layers might have been affected by whatever caused the obscuring dust cloud. It is not hard to imagine how such an alteration could take place. When Betelgeuse ejected that massive plume of gas, it shed a portion of mass from its external layers. Although this amount was minuscule relative to the star's total mass, it was still capable of influencing the atmospheric structure and the way energy travels through it. A star is not a solid, inflexible body. Its outer regions react to shifts in pressure, temperature, and density, slowly recalibrating until a new state of equilibrium is found. Throughout that period of readjustment, which can last for years or even decades, the patterns of pulsation can be modified. Another element that might have contributed to this modified behavior is the redistribution of matter within the star's atmosphere. The cloud of dust that materialized during the dimming event did not simply vanish. Instead, it expanded and thinned out, becoming a part of the intricate environment that envelops the star. It's plausible that some of this material continues to influence the escape of light from the surface, which would subtly impact the brightness we observe. This lingering presence complicates any interpretation of changes in the light curve. A decrease in brightness could signal a genuine change within the star, or it could be the result of dust passing through our line of sight, or perhaps a mix of the two. Researchers have to weigh all of these potential scenarios when they analyze the incoming data. Then there is the matter of convection to consider. The enormous convective cells that define the surface of Betelgeuse are not permanent fixtures. They change over time, merging with one another and breaking apart. Following a significant event like the one that led to the dimming, the entire pattern of convection can rearrange itself, forming new areas of rising and falling gas. Such a reorganization would change the distribution of bright and dark regions across the surface, contributing to brightness variations that deviate from the old cycles. Some data has also indicated that variations in Betelgeuse's surface temperature have been slightly different since the dimming. While the differences are minor, they suggest the star's outer layers may still be in the process of settling into a new stable arrangement. Everything points toward a star that has undergone a major disturbance and is now slowly recalibrating. Yet, there is a more nuanced reason why Betelgeuse is no longer considered normal, at least when compared to its past self. In the years that followed the dimming, astronomers have detected brightness fluctuations that do not align with its previously identified pulsation periods. Some of these variations emerge at unexpected moments or last for durations that are inconsistent with the known cycles. This is not to say that the star is becoming dramatically chaotic or unstable. It simply indicates that the complex, overlapping rhythms that once characterized its variability have been altered. One possible explanation is that the star's internal structure is undergoing a slow evolution. Stars in the red supergiant phase are anything but static. Their cores are constantly changing as they fuse heavier and heavier elements. These deep internal changes can eventually influence the outer layers in ways that only become apparent over long stretches of time. It is conceivable that Betelgeuse was already in the midst of a gradual transition before the dimming event, and the outburst merely made those underlying changes more obvious. Another theory holds that the dimming event itself was sufficient to alter atmospheric conditions and thereby modify the star's variability. When a large quantity of material is thrown off, the density and temperature of the surrounding gas are transformed, and these transformations can impact how energy radiates away from the star. Even the creation and subsequent destruction of dust can be a factor. Dust particles absorb and then re-emit radiation, and their presence can affect the temperature of the gas nearby, setting up feedback effects that require time to resolve. These are incredibly complex processes, and creating accurate models of them is an enormous challenge. While computer simulations of red supergiants are getting better, they still have difficulty capturing the intricate interplay of convection, pulsation, and mass loss over extended periods. This is precisely why continuous observation is so crucial. Every new piece of data helps to refine the existing models and put theories to the test, and Betelgeuse is one of the very few stars near enough to us to allow for such detailed scrutiny. Telescopes across the globe persist in monitoring its brightness, analyzing its spectrum, and imaging its surface whenever possible. Observatories in space provide complementary data at wavelengths that cannot penetrate our atmosphere, which helps to reveal the structure of the gas and dust around the star. All of this information contributes to a portrait of a star that is still in flux, changing in ways that are at times subtle and at other times profound. There is also a human, psychological dimension to this narrative, one that relates less to astrophysics and more to our own perception of the cosmos. After the Great Dimming, many observers anticipated that Betelgeuse would continue to act erratically, perhaps fading dramatically once more or flaring up to unprecedented levels of brightness. When it instead settled back to a luminosity close to its former state, that widespread sense of imminent drama began to dissipate. The headlines eventually faded away, and the public conversation drifted to other subjects. For astronomers, however, the star remained an object of intense fascination. In fact, its appeal may have even deepened, as the shifts in its variability hinted that its story was far from complete. The period of quiet we observe today is not necessarily a signal of long-term stability. It could simply represent a calmer interlude within a much longer sequence of transformations. If one were to monitor Betelgeuse nightly over many decades, it is likely they would witness times when it seems constant and other times when it fluctuates with greater drama. Across centuries, these patterns would probably change again and again, mirroring the slow, ongoing evolution of the star's interior and its atmosphere. From our limited human vantage point, observing for just a few years, it is natural to perceive the dimming as a singular event with a distinct start and finish. But from the star's own immense timescale, it might simply be one passage in a much longer, ongoing narrative. This serves as a vital reminder in the field of astronomy. What seems to us a momentous occurrence can be quite ordinary over cosmic durations, and yet even these ordinary processes can reveal extraordinary insights. By carefully studying Betelgeuse's present behavior, astronomers are gaining a deeper understanding of how red supergiants evolve, how their pulsations transform, how the loss of mass shapes their atmospheres, and how dust materializes in the space surrounding them. What is learned here is not exclusive to Betelgeuse. The insights extend to countless other stars scattered across the expanse of our galaxy. These are stars that will, in time, explode and seed the universe with heavy elements. So, for now, the star is once again calm, at least to the unaided eye. But scientific instruments continue to detect subtle fluctuations, small departures from historical patterns, indications that Betelgeuse is still adapting, still changing, and still presenting new puzzles for those who watch with care. What makes Betelgeuse so uniquely valuable is not simply its proximity or its brilliance, but the fact that it is transforming in ways we can observe while the changes are actively unfolding. Many stars that approach the end of their existence do so at great distances. Their final stories are compressed into brief, brilliant flashes of light in faraway galaxies. Astronomers observe the explosion, analyze the resulting debris, and then attempt to work backward, reconstructing what likely transpired in the years or centuries leading up to the event. With Betelgeuse, the circumstances are profoundly different. Here we have a massive star so close that we can monitor it year after year, meticulously measuring its brightness, imaging its very surface, and tracking the clouds of gas and dust that drift away from it. Rather than examining the aftermath, we are in the unique position of observing the slow, unsettled behavior of a star that has not yet met its final destiny, but is clearly past the tranquil midpoint of its life. This unique situation, then, positions Betelgeuse as a kind of celestial instructor, quietly demonstrating how unstable stars behave as they draw nearer to the end of their evolution. One of the primary lessons it provides is that the instability in massive stars is not a singular phenomenon, but rather a complex interplay of many different processes working in concert. For a long time, there was a tendency to view late-stage stars in fairly simple terms. The core evolves, the outer layers swell, mass is shed through stellar winds, and ultimately, the star detonates. That basic framework remains valid, but what Betelgeuse demonstrates is that the details are vastly more intricate. Convection, as an example, is not simply a background function that transports heat from the core to the surface. In a red supergiant, convection becomes a primary force that dictates the star's appearance and behavior. The enormous cells of plasma rising and falling across its surface can generate significant temperature differences, trigger eruptions of gas, and determine where dust condenses in the surrounding environment. Observing Betelgeuse has made it abundantly clear that these convective patterns are neither steady nor symmetrical. They evolve over time, sometimes gradually, sometimes quite suddenly. A region that appeared bright one year might grow dim the next, not because the entire star has cooled, but because the underlying flow of gas in that area has been altered. This has helped astronomers realize that instability in these giant stars often originates at the surface, not just deep within the core. Another lesson concerns pulsation. For many years, pulsations were seen as relatively consistent, oscillations, predictable shifts in radius and brightness, governed by the physics of stellar interiors. Betelgeuse reveals that in large, evolved stars, these pulsations can interact with convection and mass loss in ways that render them far less regular. Instead of following neat, repeating cycles, the star's brightness variations can overlap, intensify one another, or unexpectedly diminish. A pulsation that might have been minor under normal circumstances can become much more pronounced when it aligns with a large convective plume or a change in the outer atmosphere. This interplay among different forms of variability has emerged as a crucial field of study. Astronomers now appreciate that instability is frequently the outcome of several mechanisms operating together, not just a single, dominant cause. Mass loss is another domain where Betelgeuse has reshaped our perspective. In earlier models, the prevailing assumption was that red supergiants shed mass through relatively smooth, spherical winds, with material flowing outward more or less uniformly in all directions. Observations of Betelgeuse and similar stars have proven this picture to be overly simplistic. The outflow of gas is often clumpy, asymmetrical, and episodic, with massive plumes erupting from specific regions of the surface. These plumes can eject substantial amounts of material into space, forming arcs and shells that expand outward and collide with older ejecta. Over time, the environment encircling the star develops into a complex, layered structure instead of a uniform envelope. Understanding this irregular mass loss is critical because it directly influences how a star will ultimately explode. The distribution of gas and dust around a red supergiant affects the way a supernova shockwave travels, the brilliance of the explosion, and the subsequent formation of nebulae. By studying Betelgeuse today, astronomers are gathering insights that will help them decipher future supernovae, including those in remote galaxies. Then there is the matter of timescales. One of the most profound lessons from Betelgeuse is that instability is not always a sign of imminent collapse. A star can exhibit instability in its outer layers for thousands of years, undergoing episodes of heightened mass loss, surface alterations, and variability, all while its core continues to evolve at its own distinct pace. This understanding helps to correct a widespread misconception. When people learn that a star is described as unstable, it is easy to assume that it could detonate at any given moment. In truth, a degree of instability is often a normal characteristic of the late phases of a star's existence, signaling a more delicate balance between gravity and internal pressure, but not necessarily that the end is imminent. Betelgeuse offers a clear illustration of this principle, having displayed dramatic shifts in its brightness and the structure of its surface. Yet, there is no compelling evidence to suggest it is on the brink of a supernova. The phenomena we are witnessing are integral to the long, gradual approach toward that final cataclysm, rather than the event itself. Another area where Betelgeuse is providing new knowledge for astronomers is in the process of dust formation. While dust may sound inconsequential, its role in the cosmos is profound. Grains of dust offer surfaces upon which molecules can assemble, including complex organic ones. Dust contributes to the cooling of interstellar clouds, which enables them to collapse and give rise to new stars. It is also a fundamental ingredient in the formation of planets. Red supergiants like Betelgeuse stand among the most significant producers of dust within galaxies. By observing how this dust forms in the plumes and shells surrounding the star, astronomers are gaining a deeper understanding of how the raw materials for future solar systems are generated. The Great Dimming Event, in particular, presented a rare chance to see dust formation almost in real time, creating a direct link between surface activity and the creation of new matter in the space around it. There is a lesson here as well concerning the limitations of our scientific models. For decades, astronomers have been creating sophisticated simulations of stellar evolution, which integrate the physics of nuclear reactions, radiation, transport, and fluid dynamics. These models are exceptionally powerful tools, but they must consistently be validated against direct observation. Betelgeuse has demonstrated that even well-accepted theories can overlook crucial details. The sheer scale of the dimming, the specific structure of the dust cloud, and the alterations in its pulsation patterns all pointed to complexities that were not fully accounted for in earlier simulations. This does not imply that the theories were incorrect. Rather, it suggests they were incomplete, and that real stars frequently behave in ways that challenge our existing assumptions. Science, in fact, progresses through exactly these kinds of challenges. Every unexpected observation compels researchers to refine their concepts, to examine things more closely, and to formulate new questions. Betelgeuse is also teaching us something about the nature of observation itself. In the past, studying a star with such detail would have required large telescopes and highly specialized instruments, with observations often confined to small teams of scientists. The situation today is markedly different. Networks of telescopes distributed across the globe, operated by both professionals and amateurs, now contribute a continuous stream of data. Observatories in space add measurements at wavelengths that are invisible from the ground. Furthermore, computer models are now able to analyze and interpret this wealth of data in ways that would have been unimaginable just a generation ago. The study of Betelgeuse has evolved into a collaborative endeavor on a global scale, showing how modern astronomy functions not through isolated observations, but through coordinated campaigns that involve numerous instruments and a great many researchers. And there is one additional lesson, perhaps a more subtle one, but one of equal importance. Betelgeuse serves as a reminder that the universe is not a static place. Even the stars we consider to be permanent fixtures in our sky are constantly changing, evolving, shedding their material, and moving slowly toward their eventual demise. The night sky can feel timeless because human lifetimes are so brief in comparison. But the stars themselves are engaged in a perpetual cycle of birth, transformation, and death. Watching Betelgeuse over the last several years has made this cycle more tangible. For the very first time, many people have witnessed a bright, familiar star change in a noticeable way within the span of a single season. That experience has brought the reality of stellar evolution a little closer to our everyday consciousness. And as observations persist, Betelgeuse will continue to teach, not through dramatic events each year, but through the steady accumulation of information, the slow unfolding of processes that require decades to reveal their full nature. Astronomers will continue to measure its brightness, map its surface, and track the gas and dust that drift away from it into the darkness. Every observation will contribute another piece to the overall picture, helping to answer questions not only about this particular star, but also about the many other unstable stars scattered throughout our galaxy. Ultimately, Betelgeuse is not unique in its fundamental nature, only in its relative proximity. There are countless other red supergiants in the Milky Way, and each is undergoing similar processes. Each is casting off material, and each is evolving toward the same inevitable conclusion. What makes Betelgeuse so special is that we can observe it closely enough to learn from its journey. And those lessons are starting to alter how astronomers perceive the final stages of stellar evolution, revealing that instability is not just a brief prelude to collapse, but a long and complex phase filled with subtle shifts and occasional dramatic episodes. It is a phase that shapes not only the destiny of the star itself, but also the environment that surrounds it, enriching space with the very elements that will one day become parts of new stars, new planets, and perhaps even new forms of life. At first glance, the story of Betelgeuse might appear to be a simple curiosity, an interesting but distant event concerning a star hundreds of light years away and far removed from daily life on Earth. A star grew dim, astronomers studied it, and its brightness returned. It is easy to imagine that the mystery begins and ends right there, a minor chapter in the ongoing work of astronomy. But the truth is both quieter and deeper than that. The reason scientists are so deeply invested in Betelgeuse is not merely because it behaves in a strange manner. It is because this behavior touches upon some of the most essential questions about how the universe operates, how stars shape their galaxies, and how the very conditions for life itself come into being. To understand why, it is helpful to begin with something simple. Every atom in your body, with the exception of hydrogen, was formed inside a star. Carbon, oxygen, calcium, iron, all of these elements were forged within stellar cores, or created during the colossal explosions that mark the deaths of massive stars. Long before our Earth existed, earlier generations of stars lived and died, scattering these vital elements across space. Clouds that were enriched by that material later collapsed to form new stars and planets, including our own solar system. In that sense, studying stars like Betelgeuse is not an abstract exercise at all. It is a way of understanding the long sequence of events that made our own existence possible. Red supergiants play an especially critical role in this narrative because they are so massive and live for a comparatively short time next to stars like our Sun. These enormous stars have rapid life cycles, culminating in supernova events that disperse heavy elements across vast cosmic distances. The specific ways they shed mass, the behavior of their outer envelopes, and the mechanics of their final collapse are all factors that shape the chemical makeup of entire galaxies. What makes Betelgeuse so valuable is that it presents an uncommon opening to witness these very processes firsthand. The great majority of red supergiants are simply too remote for this kind of detailed investigation. We can register their brightness and analyze their spectra from afar, but we are unable to resolve the features of their surfaces or follow the individual columns of gas as they rise and fall. With Betelgeuse, however, these observations become possible. We can actually watch as its massive convection cells rearrange themselves, see dust clouds materialize in real time, and map the structure of the gas that slowly drifts away into space. This remarkable level of clarity effectively transforms a remote star into a working laboratory, and it is in such laboratories that our comprehension of the universe deepens. Another significant reason this stellar puzzle holds our attention is the way it confronts our assumptions. The progress of science is fueled not only by the confirmation of predictions, but also by moments when observations refuse to align with established models. The dimming of Betelgeuse was not entirely unforeseen, yet its depth and complexity surpassed what many theoretical frameworks had anticipated. That very discrepancy compelled astronomers to examine the underlying physics of convection, pulsation, and dust formation with renewed focus. Each of these physical processes carries implications that extend far beyond any single star. Convection, as one example, is not a phenomenon exclusive to red supergiants. It is a fundamental process in many stellar types, including our own Sun. Gaining a better understanding of how convection operates on such immense scales allows scientists to refine their models of energy transport within stellar interiors. This, in turn, sharpens predictions about the lifespans, luminosities, and evolutionary paths of stars. The formation of dust is another area of wide-ranging significance. Cosmic dust is a fundamental ingredient of the interstellar medium, shaping how light propagates through galaxies and playing a critical role in the birth of new stars and planetary systems. By observing dust taking shape around Betelgeuse, astronomers gain crucial insights into how these minute grains are created and how they are ultimately released into the cosmos. Even the star's irregular pattern of mass loss has broader consequences. The configuration of gas that envelops a star just before it explodes can profoundly influence the appearance of the subsequent supernova. This affects the light curves that astronomers depend on to calculate distances across the cosmos. Consequently, a clearer understanding of how stars shed their outer layers helps to improve the precision of the very measurements used to map the expansion of the universe. In this way, the puzzle of Betelgeuse is subtly yet profoundly linked to some of the grandest inquiries in all of cosmology. There is also something notable about the timing of this particular event. For much of its history, astronomy has been a science of looking into the past, studying phenomena long after they have occurred. The light from distant galaxies travels for millions or even billions of years to reach our telescopes. Supernovae in other galaxies are only observed after the cataclysm is over, A great deal of our cosmic knowledge is derived from interpreting these delayed signals from the distant past. Betelgeuse presents a different kind of opportunity. It allows us to see change as it happens, on a schedule that aligns with our own capacity for human observation. We can track its brightness as it fluctuates from one month to the next. We can place images taken a year apart, side by side, and see tangible differences. We can monitor the evolution of a dust cloud as it expands outward and dissipates. This sense of immediacy is a rarity in astronomy, offering scientists a unique chance to test their theories against active, ongoing observations instead of relying solely on historical records. It also provides the public with a rare glimpse of astronomy as a dynamic, living science, rather than a static collection of established facts. Many people were first introduced to Betelgeuse during its great dimming, when news headlines raised the possibility of an imminent supernova in our cosmic neighborhood. Although the star did not explode, the event ignited a wave of curiosity, drawing widespread attention to the processes that govern the life cycles of stars. For some, it was the first time they had considered that stars are not merely fixed points of light, but are instead dynamic, evolving objects. That awareness is valuable in its own right. When people can look up at the night sky and appreciate that the stars are changing, that they possess both histories and futures, it alters one's perception of the universe. The celestial sphere transforms from a static backdrop into a dynamic narrative, a story that is still unfolding and which we are only just beginning to read. The intriguing detail is that there is also a philosophical dimension to this mystery, one that can be appreciated without complex language. Betelgeuse serves as a powerful reminder that change is a universal constant. Even objects that appear timeless, like stars that have shone with steady light for millions of years, are governed by the same fundamental processes of birth, transformation, and eventual decay that define everything else in the natural world. This is not a source of melancholy, but rather a reflection of the fundamental rhythm of the cosmos, the endless cycle through which matter is perpetually broken down, reformed, and reorganized. The iron in our blood, the calcium composing our bones, the oxygen we inhale, all of these essential elements were forged inside stars that lived and perished long before our sun came into being. In the distant future, the very material of our world will be returned to the cosmos, becoming the raw material for new stars and new planets. Betelgeuse is a visible, present-day testament to that eternal cycle. It is also a testament to how much remains to be discovered. After centuries of observation, stars continue to hold surprises for us. New instruments allow us to see details that were previously hidden from view, and new observations consistently challenge our existing theories. The universe continues to reveal itself as more intricate and more subtle than we often assume. This is one of the core reasons scientists are so drawn to puzzles like the dimming of Betelgeuse. Each mystery is not just a problem to be solved, it is a gateway to a more profound understanding, an opportunity to refine our knowledge and, in doing so, to uncover entirely new questions, and questions are the true engine of scientific discovery. There is another, quieter reason this story resonates, one that is less about mathematical models and more about simple perspective. When you pause to consider the sheer scale of Betelgeuse, a star so vast it would engulf the inner planets of our own solar system, and the immense distances involved, spanning hundreds of light years across the void, our everyday worries can begin to feel smaller and less pressing. They don't become unimportant, but they are placed within a much broader context. This is something astronomy does with a gentle power. It reminds us that we inhabit a small world within a boundless universe, and that the cosmic processes shaping this universe have been at work for billions of years. To watch Betelgeuse dim and then brighten again is, in a way, like watching a distant, silent tide. It is a slow and steady movement that hints at forces far greater than anything we experience in our daily lives. And yet, these cosmic forces are not entirely removed from our own existence. The very same principles of physics that direct the heart of a star also orchestrate the atoms within our bodies. The elements that were forged in the cores of stars are the same ones that constitute the rocks beneath our feet and the air that we breathe. The connection between us and the cosmos is tangible, even across such immense gulfs of space. As astronomers maintain their watch over Betelgeuse, its central mystery will slowly be replaced by clearer understanding. Scientific models will become more sophisticated, and the collection of data will steadily grow. Some of the questions that currently remain unanswered will find their resolution, and in their place, new inquiries will certainly emerge. This is the deliberate process by which science advances, one step and one observation at a time. But even as the specifics become more defined, the deep sense of wonder does not diminish. There is something quietly profound in the realization that we are capable of comprehending any of this at all. The notion that a species on a small planet can construct instruments with the power to capture images of a star's surface, to gauge the movement of gas drifting through the void, and to piece together the life history of objects that exist for millions of years is truly remarkable. Betelgeuse is therefore more than just an enigma in the night sky. It is also a powerful testament to the persistence of human curiosity and the value of careful, patient observation. If you were to go outside tonight and cast your gaze toward the constellation Orion, you would see Betelgeuse, appearing much as it has to generations of people, a constant reddish point of light that marks the hunter's shoulder. At a first glance, nothing in its appearance would suggest any kind of turmoil or change. It would seem placid, patient, and almost permanent in the way that bright stars often do. And yet, once you become aware of its story, it becomes difficult to perceive it in quite the same way ever again. That soft crimson glow does not emanate from something quiet and unchanging. It is the radiance of a star whose surface heaves and subsides in slow, enormous currents, whose outermost layers are gently drifting away into space, and whose brightness varies in cycles that take years to fully play out. It is the light from a star that faded in ways no one had foreseen, only to brighten once more, leaving a trail of questions that scientists are still working diligently to answer. In other words, this is a star that flickers, not abruptly or sharply, but with a slow, deliberate rhythm that stretches far beyond the measure of a human day or even the span of a human life. There is a certain tranquility to be found in that thought. We tend to associate flickering with something restless or unstable, much like a candle flame disturbed by a draft. But the flickering of Betelgeuse is of an entirely different nature. Its changes are measured over the course of months and years. A single convective cell on its vast surface might take more time to rise and fall than a human child needs to grow into an adult. From our distant perspective, these colossal movements appear almost perfectly still. This contrast between the immense activity of the star and the quiet constancy of its appearance is part of what makes observing the night sky such a soothing experience. The universe is filled with motion, but a great deal of it unfolds with a gentle grace, on timescales that feel unhurried and patient. And that patience is something we can share in, at least for a few moments, simply by looking up. Perhaps you have noticed how the feeling of the night changes when you spend a little time outside, or even when you just sit by a window and let your eyes slowly adjust to the darkness. The world around you seems to grow quieter. Sounds become softer. The mind itself begins to slow down, no longer pulled in so many different directions at once. Stars like Betelgeuse seem to invite that particular kind of stillness. They are reminders that there are rhythms much larger than the ones that govern our daily lives, rhythms that are measured not in minutes or hours but in years, centuries, and millennia. It can be a deep comfort to reflect on that, especially at the end of a long day. Somewhere far beyond the view of any telescope, gas is drifting outward from Betelgeuse, even at this moment, cooling as it expands and forming tiny grains of dust that will one day become part of something new. The star is still pulsing, still shifting, and still evolving in ways that are far too slow for us to notice from one night to the next. And yet, the light that reaches your eyes tonight carries within it the complete record of all those processes, encoded in subtle variations of brightness and color, having traveled across hundreds of light years of space before arriving here, quietly and without any urgency. It is easy to forget the true length of that journey. When the light that is now reaching us first departed from Betelgeuse 600 years ago, the world was a very different place. Entire nations have risen and fallen in that span of time. Generations have lived out their lives, each one looking up at the same sky, unaware that the light they were seeing had begun its journey long before they were ever born. There is something gentle in that profound continuity. The sky does not rush. It does not hurry from one moment to the next. It unfolds at its own pace, indifferent to the passing of our days. providing a steady presence that can feel deeply reassuring. Betelgeuse, even with its unpredictability, is part of that steadiness. Its dimming was dramatic by astronomical standards, but in the greater context of its life, it was just one phase among many, a single movement in a slow, ongoing story. And that story is still unfolding. Astronomers will continue to watch the star, measuring its brightness, mapping its surface, and studying the clouds of gas and dust that surround it. New instruments will reveal new details. Models will improve. Some of the mysteries will be solved, and others will emerge to take their place. That is the nature of science, and also, in a way, the nature of the universe itself. Every answer leads to another question. Every discovery opens a new path to explore. But you do not need telescopes or equations to feel a connection to that story. Simply knowing that it is happening, that a star is changing slowly in the distance, can be enough to bring a sense of perspective. Because the same universe that shapes stars also shapes us. The atoms in your body were forged in ancient stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were created in processes similar to those unfolding in Betelgeuse now. The slow loss of material from that star is part of the same cycle that long ago made the Earth possible. It is a quiet connection, but a real one. And perhaps that is one reason the night sky feels so familiar. Even though it is vast beyond imagination, it is not entirely separate from us. It is, in a very real sense, part of the same story. If you were to watch Betelgeuse night after night for years, you might notice subtle changes. Some evenings it would appear slightly brighter, others slightly dimmer. The variations would be small, almost imperceptible, but they would be there reminders that even the most distant objects are in motion. You don't need to observe the sky each night to connect with that feeling of cosmic motion. The simple knowledge of its existence, quietly shimmering and evolving, long after we have turned our attention inward for the night, is enough. There is a peculiar comfort in this thought. The universe proceeds regardless of our observation. Stars complete their arcs across the sky, light embarks on immense journeys through space, nebulous gas drifts, dust coalesces, and new suns are ignited. The fundamental processes that sculpt entire galaxies unfold with a steady, unhurried, and continuous rhythm. A deep sense of calm resides within that continuity. It's a feeling that not everything must happen with speed, and that some of the most profound transformations happen gradually, almost without notice, across immense spans of time. This is a perspective that can help the mind settle, allowing it to release the sense of urgency that permeates so much of our daily existence. So, if you are hearing this as your day concludes, or as the night envelops you, perhaps you can visualize that faraway red star, still aglow, still in flux, casting its light through the silent expanse. You could imagine the gentle rise and fall across its surface, the immense currents of gas flowing like cosmic tides, and the clouds of dust billowing outward into the void. Nothing about it is rushed or sudden. It is just a constant, patient, and unbroken unfolding. And as you hold that image of slow, distant movement in your mind, you might find your own thoughts starting to decelerate as well, adopting that same gentle cadence and releasing the small accumulations of tension from the day. Breathing can feel easier when there is nothing left to do, nowhere else to be, and when the mind is allowed to drift without a specific destination. The night sky has always extended this sort of quiet fellowship. For millennia, people have gazed at the same constellations, drawing solace from their unwavering light and from the awareness that a greater stillness exists beyond the world's noise and activity. Betelgeuse is an element of that stillness, even with its own inherent restlessness. And somewhere, far beyond our sight, it carries on its slow pilgrimage toward a destiny that will come to pass long after we have departed, and long after future generations have gazed at that same sky, contemplating those same faraway points of light. For this moment, though, it is sufficient just to know it is there, glowing softly and flickering almost invisibly, a quiet reminder that the universe advances at its own tempo, and that sometimes the most peaceful action we can take is to simply drift with it, letting the quiet of the night settle in as the stars continue their slow, patient narrative overhead.